Alrighty, afternoon everyone. 1, 2, 3, 4, 5, 6, 7, 8. No, oh good. Afternoon everyone. We're going to start the session. They're really mama. Actually, coffee. They're actually coffee. A quick question before we start, just so I can check my numbers. I did go around requesting dinner partners. Could I have a show of hands who's coming to dinner, just so I can book? 1, 2, 3, 4, 5, 6, 7, 8 connected. 9. Do we have anyone else? I've got Andrew, Len, Rick. Now we've got Dan. Ash, Catherine, Bree, Christina, Kay, Jenny. Did I miss anyone? Beautiful. And another one there. I will book. Yep. Okay, we're close. Book one more. Okay. We're introducing, as you can see, Jenny. Oh, is your name up there?
No, it isn't. I was going to just go in. Jenny Skerritt.
Jenny, I will let. Thanks, Jenny. I'm going to let Jenny introduce herself and her role, but Jenny Skerritt from CSIRO, as on the agenda, talking about modelling in the reef. Thank you.
Thanks, Kate. Thanks for inviting me. This is the first time I've been to one of these meetings, and it's just been fantastic to see all the monitoring sites. So I'm talking about the EREFS model, but I wanted to say how important all the marine monitoring sites are for the EREFS model, and that's in terms of nutrients and TSS, because they're actually they're the basis of what we use in the model to validate the model, and together with the remote sensing, of course. But we use these monitoring sites, and we can't be without them. We can't be without the monitoring sites, and so we're really grateful for them. So the EREFS model, it actually, to do the marine water quality, we actually use the catchment model, and the catchment model from Queensland Government validates against observations, and it also includes paddock modelling and monitoring. So before we even get to the mouth of the river, all this modelling and monitoring has been done and it's been validated. So we use the source catchment model to form the boundaries of the rivers in the EREFS model. You can see the EREFS model in the background up there. That's the 4 kilometre model, and it's got the currents going in, and the EREFS model does water quality, obviously, for the report card for the Great Barrier Reef, and it also has coral seagrass, and it's validated with the observations from MMP AIMS and the remote sensing for aspects of where the river plumes go. So once we run the model, we use data assimilation, and so that's using satellite data to improve the model results. Now, the biogeochemical model is actually already very good in what it produces for chlorophyll and nutrients, but we use data assimilation to improve that extra bit for the report card modelling. I'm going to show that in a minute. So this is the new EREFS model. It now has 65 river flows in it. Previously, we had 65 rivers, but they're all in, some of them were in with just point sources, so the flows weren't included. So the new EREFS model has 65 rivers, and I should say this is the CSIRO Coastal Environmental Modelling Group, and obviously Mark Baird, Matthew Mongan, Clotilde Longley were involved in this, and of course Barbara's been involved in EREFS for 10, 12 years since the origins as well. So on the right-hand side, you can see there's the EREFS biogeochemical model on the far right, and you can basically ignore that, but I want you to notice all the forcing that we have is the meteorology. We have gas exchange in the hydrodynamic model. We have inputs from catchments, and we have a sediment model which has 4 or 5 catchment types. So this is to show you how the EREFS model, it's a different sort of model than the paddock and catchment models. It works on a physics and mathematical model. It's very much like a weather model or Bureau of Meteorology model, except it's in the water. So it's three-dimensional and has currents and waves and tides. So on the left-hand side, you can see the observations and you can see the East Australian current moving down. And on the right-hand side, you can see the EREFS model almost copying those results exactly for the temperature and also for the ocean currents. So what is the CSR Environmental Modelling Suite? It has the hydrodynamics, as I said, and the hydrodynamics includes the atmospheric forcing, river forcing. The river forcing is from presently from gauged rivers, but in the new model it'll be from the Bureau of Meteorology grid-to-grid model, which is more accurate because it includes all the catchments beyond the gauged areas in the Great Barrier Reef. And we have large-scale ocean forcing, so all the boundaries are forced with large-scale models, which are compared with observations. And we have tidal forcing. On top of that, we have waves and forcing and sediments. And one of the key things about the model is it's an optical model. And so the sediments have different optical characteristics. So sediments over coral have a whiter optical fingerprint than sediments coming from the river. And that's true for the river forcing, for the sediment that comes out of rivers, but it's also true for the biogeochemical components of the model. So we can simulate turbidity and we can simulate chlorophyll, and we can simulate them in terms of how the satellite sees them, and we can simulate them in terms of how a observation is selected. And so the BGC model has nutrient cycles, different nutrients, seagrass, macroalgae. It has 3 seagrasses and corals. And it's also got corals that are expelled by the corals now. So it's got the symbiotic and water column influence from the corals. And it also includes remote sensing reflectance. And as I said, at the end of the model gets improved with data assimilation, and so it's altered so the remote sensing observations can be included as part of the model. So this is just to show you the optical model and just to explain how the optical properties, which are very physics and mathematically based, can be used to describe the biological materials, so sediment, phytoplankton, macroalgae, coral and seagrass. So each of our phytoplankton groups has a different spectral characteristic. So we can look at chlorophyll using the optical model, and we can look at it as a satellite would look at the phytoplankton. So so on the left-hand side, as you know, as the light penetrates the open ocean, the light goes a lot deeper than it goes at the coastal waters, and certain wavelengths are lost as you go deeper through the water, as any diver would know. So in the open ocean, the spectrum goes further for all the different wavelengths. So this is an example of the EREFS model, looking at it as a satellite would view it, using those spectral observations. So you can see the brown is the brown sediment coming from the rivers, and the white suspension is from the white sediment coming from the corals. And you can go up and you can see how the model shows the different weather plumes as you go further up. And the sediment. So this is the model, and it's looking at it as though it's a satellite. I put this one in. This is an example of a Recom-like model that is used by our group, and which people can do. So you can take the larger model and you can put a smaller relocatable model anywhere you want. And so this model is over the Capricorn group. But the main reason I put this in is to show you the effect of tides. So you can see the models showing the different tides as it goes up and down, in and out, and the changes in temperature. So it's not only very good spatially, but it's good at depth to show what's happening in the marine environment. So this is the new EREFS grid. So this is the, I'm showing the 1 kilometre model, but the 4 kilometre model, which is used for the report card, is the same. And it's showing the land cells, which is sort of a mask, and all the rivers going now into the model with flow. So you can see there are some there that are in black, and there are some that are in green. So not only do we have the black 65 rivers, we've also now got, in a total, we've got 103 rivers going in up and down the coast. So it's more where the loads are the same that come out in the previous models, but now they're distributed along the coast more evenly as to where they would actually come out in the GBR. So the difference between the gauged flow that's present already in EREFS and the new addition of new rivers added to EREFS, so that in the dark, is it a pointer? It's not there. So you can see the dark columns are what was originally put into the model, and the light columns is the new flow. So in the original rivers, there's also increased flow in the original rivers. And you can see the additional flow of the new rivers, it's quite small. The additional, you can see in the lower graph, the additional of all those lower rivers, the flow is a lot smaller. Thank you. Yeah, it's a pointer, thanks. So although we've got more rivers, the best thing about it is it's coming out more evenly along the GBR coast. And these are the different, these are different nutrients and sediments that are going into the model. So you can see this is what we get from the source model. We have sediment, and in the actual BGC model, we have to divide this into 4 different types of sediment: a fluffy layer, a sand layer, a silt layer. So we divide that so that each of the rivers comes out with different layers of different types of sediment. We also get particulate and inorganic nutrients and dissolved organic phosphorus and particulate phosphorus, which are nutrients too. But we divide those particles up into refractory detritus or into labile detritus, so whether they get used quickly or whether they take a long time to use. So we have that in the model. And as I said, this is given to us by the source model, the Queensland Government model. So this is an example of the river footprints in the GBR, and we have these for all years up to present, and they're downloadable, and you can see the river traces for all years up to present. So this is the river footprint of a particularly during Cyclone Yassi, so it's a very strong footprint. The orange is the Fitzroy River, and you can see that during peak periods, not only does the river goes out slightly further into the GBR, but it also goes a long way north, and you can see it creeping up. And so this river tracer ends up even 1,200 kilometres away in the Normanby region. So all these rivers are all, when they come out, they all go north, even the Australian current's further east. So all the rivers go north. So all these rivers are influence all the areas above to the north of them. This is an example of a yearly mean river plume and the footprint extent of that during the river plume. So you can see here, the Tully is black and the Daintree is green, and this dotted line is the extent of the river plume at 1%, I think it was. So if you look at each of these sites are the monitoring sites. For example, this is Low Isle site, which is one of the what we call a pristine site, Low Isle site here. And you can see that Low Isles, each one of these is the rivers here. So you can see Low Isles, although it does have influence, a 2% influence from the Daintree at one point. Sometimes in the year, the influence from the Fitzroy is actually larger from this coming up here, during 2016-17, I should say, than the Daintree. And so also the southern rivers often influence the more northern components of the marine environment. So even though the NRM regions are designated based on land, the marine regions actually should really extend further north into what they affect. And this is the High Island site, which is just here. And you'd think that because the Russell Mulgrave is closer, you'd think that the Russell Mulgrave, which is blue, would dominate. But sometimes the Johnston dominates because of where the current takes the Johnston River. And this is to show you the effect of the Fitzroy, obviously one of the biggest rivers. And the plume extent of the Fitzroy for 2016-17 goes right up to the Pioneer River. And you can see the river concentrations that Keppel is predominantly the Fitzroy River. And even at Sandy site, the Fitzroy River can occasionally have a 2% river concentration going past it. So these are looking at all these are the actual pesticide sites. And we can do this with all the marine monitoring sites. We can see the influence of each of the rivers, the marine monitoring sites from 2010 for the 4 kilometre model up to 2019 at the moment. Actually, no, we can use the near real-time model and we can go up to this year, a couple of months ago. So we can look at the river traces and they're available on the web to look at up to recently. So you can see which river is influencing your particular site area. So this might be useful to look at the marine monitoring sites and looking at each one of them and seeing the influence of the river for particular seasons or particular years. And because we've got a historical backlog of the model, we can look at each of these. So now I'm not going to show you any nutrients or chlorophyll because that's probably another huge talk in itself, but I want to show you the pesticide tracer that we've done, the pesticide work. So again, the pesticides have come from the source catchment model and the paddock models, and we put those in at the mouth of each of the rivers. So you can see here, what I've got here is this is the model run of the pesticide Diuron at Dunk site, which was which is this one here, near the Tully. So there are two types of observation at the Dunk site. One is the water grab sampling during the flood plumes, which are the green dots here. And one is the passive samplers, which are the brown lines. And the passive samplers average the pesticides over the time that they're out. So it's an average of the pesticide concentrations. And you can see often that the pesticide concentrations are quite low with the passive sampler, even when the flood plume grab samples can be higher. Now, this is all below default guideline values, I should say. But you can see the model closely follows the pesticide low levels and concentrations. And the model's very good for low concentrations because it can actually go lower than what can be observed. And then it follows nicely the river plume extent of the pesticide Diuron as it goes through past the site. And the blue lines are where the model is averaged over the same period as the passive sampler. And you can see the blue line here is higher than the passive sampler sign, but it's still, with the flood plume, it still corresponds nicely with that. So this is the pesticide dispersal over a couple of areas of the Great Barrier Reef that I'm showing. So I've compared it against all 14 samplers, pesticide samplers that were in the model, but I'm just showing a few examples here. So these are the plume extents. So the Herbert River has a very high level of diuron in this particular year. And you can see that some of the sites are right on the edge of the plume. And because the plume follows the fresh water from the river plumes, the model or the site can miss the extent if it's right on the edge. So there's an incredibly sharp gradient from within the plume to away from the plume. So this is you can see this extends, and each of these have got concentrations of diuron from the source model in them. So this is the extent at one of the, this is an area with high levels of sugarcane, so there's quite a high concentration of diuron in this region. The Fitzroy doesn't have any diuron input into it from the source model, so there's no diuron coming out of the Fitzroy, and it would be interesting to know when you compare it against the Keppel site is actually very low in concentration in pesticides, and it could be coming up from further south from the Mary even. So you can see the concentrations from the Proserpine, O'Connell and Pioneer are quite high for this region. So what can we use the model, when we validate it against all the pesticide monitoring sites, what can we use the model for? So we decided to show the diuron plume surface area, so where diuron is greater than 2 proposed threshold values. So if we use a more stringent guideline of 0.075 micrograms per litre, up to 1,400 square kilometres of the GBR can exceed the diuron threshold. And if we use the proposed guideline values of 0.43, up to 400 square kilometres of the GBR can exceed this threshold using the model. So you can see it also goes down to 0 as well during the dry seasons. And to take this further, we used the mapped seagrass habitat within the diuron plume. So we took observed seagrass and we put it into the model, and then we looked at where the diuron plume extent proceeded. So you can see here, in order to get an idea of what the value is, so this is 5% of seagrass, all seagrass habitat, deep and shallow in the Great Barrier Reef here. And the more stringent guideline has up to 175 square kilometres of seagrass habitat where it exceeds the diuron threshold, and the proposed guideline value threshold has up to 25 square kilometres of seagrass habitat. Now, although that, it seems like a lot to me, but although that doesn't seem, even though that's 5% of seagrass habitat, the actual 25 square kilometres of seagrass exceeding diuron threshold could be significant, because the seagrass is the one close to the coast, and that's where the river plumes go. We also did the same thing for all the coral. So we mapped the observed coral into the model, and we looked at the diuron plume for the observed coral. Given that this is observed coral, not close to coast coral, only 0.25% of the coral habitat is this yellow line here. Up to 60 square kilometres of coral habitat can exceed the diuron threshold using the stringent value, and up to 20 square kilometres of coral habitat can exceed the diuron threshold for the less stringent value. But 60 square kilometres, when it's all close to the coast, is quite a huge area that can be impacted if exceeded, the threshold can be exceeded. Yes, so this is on the right is an example of the dispersal of the diuron. This is actually very, very low, so this is well below threshold levels, just to really show you the extent of the diuron as it comes out. really see that well. And there's some in the Burnett Mary too, I should say as well. So these are the people involved in the new BGC model, and the GBR1 and 4 new BGC model will be used next year with the new paddock model and the new catchment model. And Clotilde and Matthew are just finishing the hydrodynamics of this, of the GBR1 and 4 model, and it's currently running at the moment with the geochemistry. And of course, we couldn't do it without the GBR dynamic SEDNet modelling team, which is also called the source modelling team, and they're very involved in both our nutrients and our pesticides that we produce. And that's it. And
Do you want me to address the reinitiation?
We worked with Jenny, hello, online. We're just going to address the reinitiation of pesticide question. In other words, some people didn't realise that it had dropped out for a year there, and we were very keen to get pesticide monitoring back on as soon as possible. And one of the reasons that it did drop out for the moment was that we were waiting for the modelling, because there wasn't, it was previous to this team, but there was some uncertainty, as Jenny has pointed out, about the locations of the sampling sites actually missing the critical plumes. And so therefore the cost effectiveness of this program came under scrutiny, et cetera, and gradually it got whittled down to only the areas of potentially highest risk, which was wet tropics, Mackay-Whitsunday, and then finally only Mackay-Whitsunday. So we were waiting for the new pesticide modelling, and what we've done to get it up and running this year is we actually contacted Jenny, contacted our partners, contacted Des, contacted the catchment team, and everyone associated, including Rachel sitting there at the front. She was absolutely instrumental in having this put through the ISP, the Independent Science Panel, and we asked them on a very limited budget at that time, what were the critical sites to A, validate the modelling, and B, capture those high risk catchment areas along the coast. So that's how we came up with the current sites. But after this year, we'll be doing another reassessment, right?
Yeah.
Absolutely. So we tried to put in, with poor Jenny, she said, how many sites can I have? Can I have that one? No. So we came up with 11 sites. It's been some unexpected difficulties in actually getting them deployed for various reasons, because changing their locations did put them into hard to get to areas, particularly in the Mackay-Whitsundays. So we finally got 10 out of the 11 sites out there deployed almost already. Where's Trotwater up to? We got all of them out? All out, yeah. Yippee, we're all out. So that's how that came about. So this year is the first year of reinitiation. Yet again, thank you to people that are helping out with the funding. They're called DQ, thank you. Because this was just done on a very limited budget at this point in time for reassessment. But it's certainly looking at your information, particularly about the Diuron. I know there's new, Rachel has just informed me too and reminded me there are new draft critical, what do we refer to them as? Default guideline values, thank you. So they're coming out, so we will be talking between us about those again too. But that was really wonderful to see, yet again, the stuff we could have up on that dashboard showing us we're going to be backtracking and looking at previous pesticide sampling results now in light of the fact that, in fact, it's probably not coming from the rivers we thought they were coming from. Okay, they're being influenced by rivers from the south. So that's a really interesting point.
And that holds for nutrients as well. So a lot of the nutrients from the south go up and affect the north as well. And yeah, the importance of two types of observation is just fantastic. The passive samplers and the grab samples is just a wonderful thing to have, two different sorts of measurements.
Give us a quick brief on your BOM interpretation of why we need monitoring and modelling.
The BOM, you mean SIRO?
Yeah, Jenny does this really great thing about, you know, most of our weather is forecasted via modelling, right? But we still have weather stations all over the place.
Yeah,
so.
yeah. And the thing is with the paddock modelling and the catchment modelling is that they're often, the farmers and agriculturalists are often just say, oh, it's just a model. But if they don't get those results correct, if they don't get the nutrients correct, then it won't be correct once it comes out at the mouth of the river into the marine model, which works the data in a much more mathematical and physics-based way. So it actually helps them talk about their model in confidence that they're actually doing the right thing. And because farmers trust Weather Bureau models more than, not always, but they do tend to trust Weather Bureau models because they are physics and mathematically based, and just they understand the way they work because we've had all that education about how meteorology works. And so this model is very much like, the EREFS model is very much like the Weather Bureau model, except it's in the water. It's got that, the physics I'm talking about, the hydrodynamics and the physics of it. The biology's more interrelated, so it causes more difficulties, but yeah, the physics and the mathematics of it is it's very sound and yeah, as good as a weather model.
Brilliant. Thank you, Jenny. Steve, you're on again. Say it again.
I can relax. I'll go for another. Hello again, everyone. Again, thank you for having me. Good afternoon, everybody in the room and online. I don't know, just thanks for Kay and Martina for inviting me to talk this afternoon. I don't know if they'll live to regret it because this is really one of my pet passion areas that I really love, and I could talk for hours and hours on this, but I'm going to try and be very, very disciplined today. But yeah, really looking at establishing these long-term climate and environmental records for the Great Barrier Reef and some of the insights we've got over the past. And I just think about, in your mind, what sort of long-term records are useful for us to understand the baselines in the Great Barrier Reef and, understanding the condition of the Great Barrier Reef and how that may have changed over time. And I've always been intrigued, sitting in a lot of different workshops and areas over the years, that everyone has a very different perspective of what a baseline is, like where do we compare our current data with the data back in time. So I'd imagine, if we put it to the seagrass crew, Len and Kath, what's a good baseline for the seagrass? They might tell us, oh, well, actually, maybe it's 2006 at the start of the marine monitoring program, because that's when we've got the really comprehensive data all the way up and down the Great Barrier Reef area. If we put it to like Caroline Pettis, our remote sensor, well, she'd probably say, our baseline's 2002, because that's when the satellite imagery data sets start, and the coral records maybe the first big systematic monitoring from AIMS back in about 1986 from the long-term monitoring program. But then, of course, you go to like the modelers with the source catchments and EREFS. Obviously, the pre-European, pre-development, pre-arrival of Europeans is probably, the baseline that we would think about. And then maybe a geomorphologist, geologist, which I'm probably more in that field, we might say, no, we need to go back, thousands of years or so. But I guess in what I'm talking about long-term records here today, I'm talking about records probably at least 100 years plus type records that we'd look at. And just off the top of my head, some of these records of the, the drivers and pressures we'd like to understand, I'll just flash them up on the screen. I won't mention any of them in briefly. Some of these would be, really useful records. And in fact, most of these, we've got some insights on how these records have varied over time and like through little windows of time at least. Some a lot better than others. But of course today I don't have time to really talk about all of these records, so I'm just going to cover 3. I was going to try and cover 4, but I I realised I needed to cut one. So I'm just going to, and these are the 3 records that I've probably been most involved in the work that I'm comfortable to talk about as well. So we'll cover land use change, the discharge, and the sediment and nutrient loads changes. So I'll start with the land use change. This is a bit more fresh in my mind, that a resource that we just got out last year, and I think I can finally start talking about it. I've had enough therapy sessions, so it's almost like going back, doing your PhD all over again, just the relief to have that work out. But I just put that up there as a special shout out to Beck Bartley, because I've been tinkering, compiling these land use records for several years, and I sort of ran out of steam and had a lot of the data together, but there was still so much more work to go. And through a partnership with CSIRO and Tropwater that Beck Bartley initiated, actually allowed me to have the time and resources to go ahead and actually complete the work and get it out there. And so, it's not in the back of my mind all the time. So what's a data set that we have? Well, actually for Queensland, there's annual statistical registers that go back to 1860, and the data reported pretty much annually from 1860 to 1997, and then after 1997 it started to be 5-yearly reported data, and they report data at a district level, and that's just an example of the 1873 statistics and all the districts in Queensland back in the day. And this is the livestock numbers of the top: horses, cattle, sheep and pigs, right? But there's all this extra data out there on cropping areas and the different types of crops and mining and all sorts of things that are there at our disposal. And I always, the reason I got into this was kind of like, well, why don't we have this foundational data set of the land use change? There has been records published in the past, like Maria Gilbert and John Brodie published the land use change for the whole Great Barrier Reef catchment area, but not at the basin scale. And there's been a couple of individualised sort of basin sort of compilations that were being done, but none for the whole Great Barrier Reef catchment area. But it is a bit of a job, and you go back through the districts, and the next thing that you rely on is there's these beautiful old district maps where it shows you where the districts were back in the time. And I guess this slide doesn't probably give those maps, the greatness they deserve, because when you've got them in front of, they're really quite attractive maps. But another one of Beck's brilliance, we had Anne Henderson from CSIRO, who's a great GIS person, who then converted those maps into our nicer GIS style maps that get overlaid then with our river basins and our NRM regions. So then we can start allocating that district data to a particular basin. And of course, so that, that really helped things out. And it was really a tricky process, because the statisticians, they change, the districts split over time, they change, sometimes they get grouped back into one, they change their names, and you've just got to be onto it every year to track how those districts have changed over time. And that's like an example of a flow chart for just the Burdekin and NRM region and how they've changed over time. The Burnett, Merri and Fitzroy are even more horrendous than this. There's so many more districts down that way, but we've got them all in finally. So I'm just going to quickly try and flash through it. It's probably a bit death by graphs, but just to give you a bit of an idea of the different types of things that we compile for this work so we've got the population for the whole Great Barrier Reef catchment area, but then we've got the NRM region, and that was just within the paper itself. But in the supplement, we go down to that basin level data, and you can download all the raw district data if you're that interested, or just the basin level data if you're interested in that. So population, this is the livestock resource. So we didn't compile the horses and pigs, we just did the cattle and sheep, which are the main livestock. But this is the Great Barrier Reef catchment area up the top, the cattle by the NRM region, the sheep by the NRM region, and then the stocking rates there as well. So, and how they have changed from, again, 1860 up to 2019 there. And you can see, like some of the big expansions in the cattle there, in the 1960s, 1970s, which corresponded to the clearing of the Brigalow lands, as well as the big declines with some of the really big droughts in the catchment area as well. Then we've got the total cropping area for the Great Barrier Reef catchment area, NRM region, And then when we subtract the total cropping area from things like sugarcane and cotton and bananas, which are the other crops that I calculated, you sort of get an estimate of what was going on in like grains and horticulture. And particularly when we go down to the basin level, you know, you can separate, you know, the horticulture in the Barron and the Don from, you know, probably the grains in the drier catchments like the Fitzroy and the Burdekin. Sugar area, banana area by NRM, so you can obviously dominated by the wet tropics there, but interestingly, you know, the Burnett Mary had some bananas growing in there in the 20s and 1930s. And then the cotton, and then now we sort of go down into the basin sort of level just to show you, now you go into that finer scale level. So this is just an example for the Burdekin population, you know, the sheep and cattle numbers and the cropping. And we could go even into the sub-basins. So for the Burdekin and the Fitzroy, because they're such large basin areas, we split it down into more of some of those sub-basins. So for the Burdekin, as an example, we split it into the Upper Burdekin and the Cape, Ballyeanday, Sutter in the southern regions, and that sort of more coastal Burdekin of the Bowen, Broken, Bogey, and the Lower Burdekin sort of delta. And again, you know, you can sort of see those more finer scale level detail when you do that, like, you know, in the Upper Burdekin, the population was booming in those gold rush days when Charters Towers and Ravenswood areas were going nuts. Now there's less than half the population in that area. You know, you can sort of see in the sheep numbers, the sheep were primarily or predominantly in that southern Ballyeanday Sutter catchment, never in the Upper Burdekin or the coastal Burdekin. So it gives us that sort of level of detail. And then, of course, area under crops, most of the grain cropping is happening in that Ballyeanday Sutter part of the Burdekin in the southern, and the sugarcane, of course, in that lower Burdekin area. So that's all that in a quick nutshell. Hopefully I covered that fairly quickly. Now this next slide is like a segue into the next section, because we're starting to understand what's going on in the catchment, and that's obviously influencing our discharge and our loads going out to the marine environment, which, you know, is obviously the loads going out there happen in these big flood events. So this is the satellite image from the 2019 flood from the Burdekin. What resources do we have to map that change in discharge and the loads that we can produce? And here, one of the best records what we've got is our coral cores that we can collect. And the first one I'll go into is the coral proxy records of river discharge. And what we use are Porites corals. These are the massive brain type corals that can live for several hundreds of years. They lay down annual growth bands like trees do, and they're regularly growing their skeleton from the surrounding seawater. So they're preserving a record of that seawater chemistry at that particular time. So when we take a big coral core of the coral, the cores look a bit like this, and we take a slice of those corals, and then we can start analysing them for different components. So one of the first things that we can do is that with this core slice is to put it under an ultraviolet light. And this is what the core slice looks like. This is a core from Havana Island collected in 2012. That's the upper part of the coral. And you start to see these really bright yellow lines just glowing out of the coral, right? And we can measure the intensity of those yellow lines, and they are directly, strongly correlated with the river discharge volume from the neighbouring adjacent river catchment there. So we can actually get that correlation and do a reconstruction of river discharge over time. Just to work you through it, so this is the core, as I said, taken in 2012. There's a big river flood for 2011, smaller flood in 2010, really big Burdekin flood in 2009 there, big flood in 2008, smaller flood in 2007, but still fairly sizable. And then we get a period of much drier Burdekin years, a couple of big floods towards the end of the late 1990s, and then here's the big 1991 flood here. And when start looking at these coral records, they're so strong, some of these lines, that you can just, once you get your eye and you can just pick out the big floods from the Burdekin, and you can say, there's the 1991 flood, there's the 1927 flood, there's the 1870 flood, you know, and you can work off your chronology from there. Anyway, so once we've done that, we've correlated it with the measured flow from the Burdekin, we can produce our reconstructions like this one for the Burdekin River, which goes back to 1648. So you can sort of see how the river discharge has changed over this whole period of time, right, from 1648 to, I think this is about 2012 that it goes up to. If we put some more quantitative numbers on there, right, this is looking at 100-year intervals in the coral. So this is the first 100-year interval from 1648 to 1747. And the median discharge over this time that we've reconstructed for the Burdekin is 5.5 gigalitres. The 10th percentile discharge is 2.4 gigalitres, and the 90th percentile discharge is 12 gigalitres or 12 million megalitres. You can see fairly similar, a little bit lower maybe in the next 100-year period from that 1748 to 1847 period. But in the last sort of 150 years, you can see there's been some big changes to not just the median values, but the 90th percentile floods. So essentially the key story here is the floods from the Burdekin have got much bigger. So, you know, the median's gone up by about 1 gigalitre, but the 90th percentile values have gone from, you know, 10 to 12 gigalitres now up to 22 gigalitres. So what's the key point of there? Bigger floods can obviously expose larger parts of the Great Barrier Reef to these flood plume conditions, right? The next part of the final part of this story is when we start looking at the annual return intervals of these big floods, these 90th percentile flood intervals, we see the annual return interval for this first 200-year period of the coral record changed from about, you know, the 10 to 12 gigalitre events were happening at a frequency of 1 every 14 to 20 years. And now the frequency of a 22 gigalitre event for the Burdekin is now happening once every 5.8 years. So again, I suppose stepping back, the floods have got bigger and they've become more frequent. How does this compare for a much longer time series back? So now we go back to, these were corals collected from Nally Bay in the Nally Bay Harbour development. They unearthed these fossil corals that died about 6,000 years ago, and they lived for a period of about 200 to 300 years. So when we look at the luminescent line records from these, the luminescent lines look quite different to the current Burdekin, where you see that one big sharp line generally most years. If we have two big flood events, maybe you'll get to see a double line, but generally that one big sharp line. With these ones, we see like multiple lines that are a lot weaker, but almost all the way through the year. So it tells us back in this period of time, about 6,000 years ago from the Burdekin floods, that actually there was less seasonality in the Burdekin flood. There was a lot more, the waters were coming out over a much longer period of time. And if we have a look at those sort of statistics again, this again is a reminder of the instrumental Burdekin record, which we've got back to 1922, we've got measured flow from the Burdekin. Again, that median value is 6.6 gigalitres, the 90th percentile is 23 gigalitres in that record. If we look at this record from the mid-Holocene for the Burdekin, the actual, didn't come up, the long-term median for that record's about 3.1 gigalitres, but there's very little variation between that 10th and 90th percentile values. And if you were to say to me, Steve, here's a record, from a river in the Great Barrier Reef, today, where would that be? And I would look at that data and say, oh, that would be the Tully or the Russell Mulgrave. They're the most, least variable rivers in the Great Barrier Reef catchment area. That sort of record looks pretty similar to that. So you can see the Burdekin discharge has probably changed quite a lot over the years. I know I've been very Burdekin-centric already, so just to shift away to make everyone aware that these luminescent line reconstructions also exist for the other major rivers of the Great Barrier Reef catchment area, including there's a reconstruction for the Fitzroy, but there's records, I think, for the Herbert and the Tully and other regions as well. And then if I just shift back to combining the discharge records and the land use records, we could start doing other really neat things like looking at reconstructing dissolved inorganic nitrogen loads over time. So this is just an example of what we're working up for the wet tropics region. We know that this is the annual discharge record from instrumental gauging more recently, but then going back to the luminescent line records that we've got from the coral luminescence records. And if we couple that with our land use, the actual DID measurements that we have from, different land uses and show a very strong correlation with the amount of fertiliser applied and the amount of discharge for that year. So essentially we can do a reconstruction of how the DIN loads have changed over time. And, you put that against some of our other land use data like the sugar area and the nitrogen fertiliser applied sort of data, we can start producing those type of records. And then indeed these records start, fitting into those loading maps that I presented a little bit earlier for DIN. We use this sort of model to project what the DIN loads were for the wet tropics and, now, and we know what roughly the baseline load to predict what the pre-European or pre-development load was to inform our loading maps. So moving into my third one, which is the coral geochemistry. So now we're taking that slice of coral and we're either drilling it out and analysing the carbonate skeleton for its chemistry, or we can put it under a laser ablation machine that ablates the skeleton at much finer resolution and gives us like a scan of the chemistry. And I started with the barium calcium record from Havana Island. This was the record that really changed a lot of things in water quality and it came from Malcolm McCulloch now and his team nearly 20 years ago. This is the same coral record that the luminescent line record comes from for the Burdekin River that I just showed earlier. And what this record showed was a large increase in the barium calcium ratios after about 1870. And, it sort of increased in values of about 5 to 10-fold. Now, the initial interpretation of this record was this was directly related to increased sediment flux from the Burdekin of about 5 to 10 times, right? And so I looked at this record and I thought, oh, this is wonderful. It finishes in 2000, but, if we go out and collect some more cores of this, if we can relate that, we've now got measured loads from the Burdekin River that go back, 20 plus years. We can start doing a correlation with the measured sediment loads and the barium calcium ratios and produce a annual sediment load reconstruction for the Burdekin. How neat would that be, right? So that's what I got right into it. And unfortunately, it's actually, I think, more of a record of freshwater going out into the Great Barrier Reef than sediment. But we needed to tell that whole story, we needed to really tell the full catchment to reef story, which is where monitoring came in again, right? So if we look at a big catchment to reef investigation of the barium in the corals, when I was out sampling flood plumes for some of the early marine monitoring program efforts, I was cheekily collecting some dissolved metal concentrations as well over the salinity gradient. Now, the theory with the barium calcium records and how it works to reconstruct sediment loads is that when the clays in the river meet the very first, starts to mix with the very first saline water, it hits higher ionic strength and the barium gets detached from the clays. It gets released from the clays and dissolved into the seawater, and then it's carried in the seawater and it gets sucked up and incorporated into the coral. So if you get more clays, obviously you're going to have more barium coming out off those clays and it goes offshore. If that's the case, you would expect this scenario to happen. So this is the barium, and this is dissolved barium calcium. So we've filtered the water sample from the sediment, just looking at the dissolved concentrations. And this is the trend that you see in the Amazon River plume, right? So you have the dissolved barium concentration starting at about 100 nanomole, and in that 0 to 5 salinity zone there, it rises up to 200. That's the barium coming off the clays, and it's more than double the concentration. So a significant amount of barium's coming off the clays. It's then mixing all the way down, and your coral might be growing in here and recording that change. And if you have more clays in the water, maybe that would go up to 400 and the curve would come down there and that same coral would record, that higher value. And that's how that record was interpreted. But looking at the data that we had from now 5 flood plume periods over that salinity gradient, there's no real strong evidence of much desorption happening of the barium in that estuarine mixing zone at all. And the other really interesting thing is the variation in those barium concentrations at the end of the river are quite high itself. in that zone. So this is just some of the extra. Then now we go into the catchment monitoring stuff, where I was involved in monitoring the tributaries of the Burdekin back in the day and took some cheeky ad hoc samples from the major tributaries of the Burdekin. And we've got samples from, concentrations from about, 1,500 to 2,000 in those upper tributaries. Less sampling from the Bowen. The concentrations looked a bit lower there, but not a lot of samples. But then the sampling at the Burdekin and Inkerman site, our end of catchment site, you can see the variation in those dissolved barium concentrations at the end of the river. So really, I think what's going on here is it's that variation in the dissolved barium concentrations just makes this record quite messy, and probably more related to freshwater discharge rather than the sediment. And this is other monitoring. We did monitoring of the event at the end of the Burdekin River in 2016, which was the floodwaters produced from Tropical Cyclone Debbie. And you can see just the variability again in the barium, which is these green markers here, and this is the total suspended sediment data. When the total suspended sediment data peaked here, coinciding with roughly the peak flow of the Burdekin, the barium concentrations were the lowest measured that we've got. So not really related there to the TSS values either, but then it shoots straight up on that falling limb of the hydrograph and starts going down, and it's like a reverse hysteresis pattern if you plotted the discharge versus the barium concentration. So that's the sort of first line of evidence to say, well, probably it's not a sediment indicator. But saying that, look, I don't want to knock at that record, because it's still an incredible record, and it's a record of, increased terrestrial exposure, I'll say. And that's what a lot of the literature that's studying the barium calcium ratios in corals now are starting to use those words, terrestrial runoff rather than sediment runoff, because we probably think it's more related to the freshwater. So moving out into the marine environment now we took a lot of cores, Nelly Bay, NEL, Pandora Reef, Havana Island, Pelorus Island, and there's a few more actually. We cooked more in Jeffrey Bay and another one each, and the barium actually in those records didn't coincide with the flood, so we're recording something completely different. So it was almost like the coral that you picked, but that's another story, and I can never explain that complexity of that. But the records that did record the Burdekin River floods, they sort of agree, with the samples closest to the river mouth from Nelly Bay had much higher peaks than the coral cores further away from the river mouth at Pelorus, and they were sort of faithfully recording those flood events. But a bit of a change in the peak since the Burdekin Falls Dam, which was quite interesting as well. Now, we know the Burdekin Falls Dam trap a lot of sediment, but that also reduces the daily peak discharge from the river, which I think from a hydrology perspective is also pretty important. Anyway, I'm going to zoom in onto this section here, because the trouble is how do you decouple the barium calcium ratio from terrestrial discharge, from freshwater and sediment, right? And these periods just happen to be really nice, because 2008 had a relatively, high discharge with extremely high sediment. This one had high discharge with sort of pretty high sediment, and this one had even higher discharge with quite a lot lower sediment load. So I was thinking, well, these three would be good. And I can tell you, I really tried hard for this. I really thought this was going to work, and this was quite heartbreaking for me. And you can just see the amount of silliness I went to try and quantify the barium in these parts. So this is the barium calcium ratio scan for that sort of 5-year period, just focusing on those three major events. And I took readings of the barium in the year, so over the whole water year, and that's those arrows up the top, like an average barium calcium over that year. I took the peak barium values for those years. I looked at the average barium values for the period where the elevated barium calcium concentrations were in the coral, and took an average of that. And the one I really thought was going to work was this area under the curve type barium calculation that I did, that showed some really promising results at the start. But then when it started to compare it to the measured loads, so this is the measured loads from the Burdekin, 2008, nearly 15 million tonnes of sediment. 2009, nearly 11 million tonnes, and then down to 6.2 million tonnes. So, you know, if the barium was recording that sediment faithfully, this, you know, should be almost threefold higher than the barium in that part of the coral, and it just doesn't happen. And there's the discharge records. So in a nutshell, you know, it goes to a lot more complexity than this, and I know I don't have time to go into it, but, you know, you can sort of see how the water comes out in these big flood events, you know. So this is the daily discharge now, nearly 35 gigalitres of water in 2011, but you can see it came out in 3 events. So the peak water flows are a little bit different to what we saw in, you know, 2009 and 2008. So it's almost the way the water comes out of the river and the way the water moves in the marine environment, which of course we track in the marine monitoring program. And coincidentally, I know Mark Biard has done a bit of work on this, and he actually can, you know, match up pretty well with the plume exposure at that particular site with the barium calcium concentration. So I think it quite works pretty well. I don't have time, again, to go into this in any detail, but this is the relationship of the peak barium calcium ratios with the peak weekly discharge from the Burdekin and the peak annual peak with the annual discharge from the Burdekin. And so for some of the big flood years, better recorded on the curve depending on whether you use the weekly or the annual, because, you know, some of those years like 1991 where there were 2 big flood events in the Burdekin is better recorded in the annual, and, you know, a bit of an outlier in the peak 7 days. But saying that, there's still a few other outliers which I think are more like 1981 stays way off the chart, and I think Eric Wolanski actually had some data from this, and it looks like the Burdekin plume went straight up north and was really concentrated right over Havana Island. So it was almost that scenario where the perfect storm where it just went right up there, and Havana Island was really strongly exposed to those, you know, less mixed waters from the Burdekin. Somewhere like 2009, which falls on the other side, the plume actually moved away from the Havana Island site. So in some ways that site was less dosed with the plume water. So I think this is what the barium is really recording. Sorry to let you down. It's not, I don't think it's really a sediment indicator. However, there are still some disputes, and it'd be remiss of me not to say that Malcolm McCulloch and his old postdoc student have just published a paper this year to sort of argue against, you know, put forward that it's still a sediment flux indicator. I'm still not completely convinced, but the one thing that sort of still doesn't quite sit well with me is, as I showed you with the luminescent line records, it shows like a doubling of discharge, like a 2-fold increase in the luminescent line record, whereas the barium calcium record increases by 5 to 10-fold. So if it was primarily a freshwater record, which I think it probably largely is, you know, there's still a bit of a decoupling. And what this study tried to do was actually decouple that, you know, get the relationship of barium with the luminescent lines and then plot the residuals and look at the difference to say, well, maybe we can separate that floodwaters from the sediment. So still a work going on. Now, I know I'm starting to go over, so I probably don't have time to go through this. This is a coral manganese record from Magnetic Island, which really tracked that land use change. This is when I first started getting into the land use change data back in about circa 2005, I think it was. But essentially, this was a record, I think, of topsoil erosion from the Burdekin. We see the manganese just going nuts in the coral pretty much straight after the first introduction of livestock in the Burdekin. And once that topsoil, manganese-rich topsoil is removed, we're back down. But hopefully I've got time to talk about something into the future, because one of the really exciting ones is the rare earth elements in the coral, right? So this is the Burdekin discharge again. We go back to 1988. And you have a look at some of the records, like the total rare earth elements to calcium and the neodymium to ytterbium ratio. So this is like a ratio of a light rare earth element to a heavy rare earth element. You start seeing, you know, spikes coinciding with these big flood events and big sediment loads from the Burdekin, but also, you know, upsettingly, you know, like the peak for 2011 is just as high as for 2009 and 2008. But of course, in 2011, we had Cyclone Yasi as well. And I think the rare earths, not just record, you know, the extra loads coming from the rivers, but they're recording more like a sediment exposure record. So they're recording those big resuspension turbidity events that would have been associated with the cyclone. And indeed, you know, when you look at the Nulla Bay Harbour, when they were dredging that harbour out, we actually, you know, not much flows going on from the Burdekin, but we start to see some of the spikes in the record potentially responding to that. And with the capital dredging program, well, the last capital dredging program in the mid-90s in the Townsville Port area, we start to see some response to the corals potentially to that sort of exposure of the sediment. And, you know, guess what this record is? This is I'm not going to say our, this is AIMS's marine monitoring program turbidity logger in Jeffrey Bay. This is a coral from Jeffrey Bay. You know, this the coral was taken in 2012, and now, of course, thanks to, well, I'm going to shout out ARENA here. Yes, no, I was going to do that, Dan. ARENA for getting these turbidity loggers out there. We've now got nearly 15 years of continuous turbidity loggers data, and you can see those spikes. You know, 2011 actually had the highest spike, so it's not just reading, I think, the sediment coming from the Burdekin River, but also that resuspension from Tropical Cyclone Yasi as well. And these records are starting to match pretty well up with it. So I'm thinking, you know, continuing with the coral core records, something like this could become the big proxy of, you know, sediment exposure for the Great Barrier Reef that we could develop over the long term with the use of this long-term monitoring data, which we now have, you know, 15 continuous years of data. There are 4M records. I probably don't have time to really go into this as a bit of an alternative to corals. Kay's shaking her head, so ask Martina in the afternoon tea break because she's the expert on this, but they show some promise. There's, you know, we can see some potentially big changes in the 4M index in the Mackay-Whitsunday region in the last 150 years, but no such change seems to have occurred in the Havana, Pandora Reef records. And this is really my final slide, Kay. This is really the big, you know, picture thing that I'd really like to talk about, bringing all these long-term records together and telling that bigger narrative of the catchment to reef connection in water quality, right? So now for the Burdekin Basin, sorry, I'm going Burdekin-centric again, but, you know, we've now got really good biophysical records. We've got, you know, mercury spikes in sediment cores offshore that coincide really nicely when gold was starting to be mined in the Burdekin catchment and the use of mercury. You know, we've got, you know, wouldn't it be great to have a really good sediment load record? We've got our sort of coral records, as, you know, this is the barium, calcium and manganese records. Now we've got the area of cropping, we've got mining to line up, the livestock records, population, we've got our river discharge and river reconstruction discharge that goes back a long time. We've got our basin rainfall data. So we could start, you know, putting all these time series together and start telling that really bigger narrative picture of the environmental history really from across the catchment to the reef. And I will leave it there.
Questions? Blown away?
I have a comment rather than a question.
On time, too. See, on 2:10.
I know, you did well.
No questions? I was going to ask, do people want to head straight into seagrasses? How's your behinds feeling? Do they need to stand up, or because people have to go, and I was thinking if we get lens in before people have to go, then they actually get to see the seagrass. Might miss some corals, sorry, Angus, but there's only a couple of people that are going. I don't know. What do you think? Or do you want break now and too bad, too sad?
What about a shorter break?
A shorter break?
I do have a comment about his talk though.
Oh, good. But what do you think about that idea?
Yes, I like it. Yeah, that's fine.
Shorter break?
Yeah, shorter break. Yeah, that's fine.
All right.
We also try to validate the barium calcium as in foreign researchers, barium calcium and the magnesium calcium in terms of temperature. And what we found out, so depending on the condition of the species you're analysing, then you would get those differences in the barium calcium. And I wonder if you guys have thought about that in terms of corals.
So when we started doing those, we got all these calls. I think Cassie might have even come out on one of those trips. Did you come out and get like photos for me? I can't remember if it was that trip, but with those records that I just showed, we actually took 10 cores. We took 2 from Nellie Bay, 2 from Jeffrey Bay. Well, we took more, but I analysed 2 from Nellie Bay, 2 from Jeffrey Bay, 2 from Pandora, 2 from Havana, and 2 from Pelorus. I'm thinking, this is going to be really great replication between the sites. And at all the sites apart from Jeffrey Bay, which neither of them recorded the Burdekin discharge, there was just terrible replication. One coral was faithfully recording the Burdekin floods, you lined up. The other coral was recording something completely different. And we started thinking, oh, maybe, it is a species thing. And we had the GPS points we happened to have a nest site at Havana Island, which was nearby, where we got these 2 cores from Havana, from there, which were pretty nearby. And think, is it a species, difference in the coral that's, recording it and one's not? And we went out and, got some extra photos and samples and things like that. And I got onto MRA Turak to do some identification. And then it started to become, there's a lot of disputes on identification of Porides species. And there's so many, all the expert taxonomists don't agree on what. So I got told they were both probably Porides latea, I think it was. And probably the same species, but we could never rule that out. And, and I don't. Yeah, well, we could go to the genetic level. Like I got, I ended up going as far to try and solve that, but MRA wanted a scanning electron microscopy image of the corallites on top. So I actually got a slide made up of both of those Havana corals for him to look at. He was like, oh, these are beautiful. But no, I still can't tell it there, whether that's that or that's that. So I was like, no, I'm not a coral taxonomist, so I'm going to step away right now and leave it to the experts. With it, yeah. Mm.
What other possibilities? That was the first thing that came to mind to me, was these
Well, just those locations, is there any, Nellie Bay corals is a little creek.
Mm. Gustav Creek, yeah. So there is probably, on that record, there is probably local influences. That's why it's a little bit high, but also because it's closer to the mouth. Yeah. Yeah. Well, the other thing with those records, while one worked and one didn't, one of the insights was in the coral geochem is, for these ones, the change in the coral geochem around that time from when I did an earlier one was you had to basically treat the coral pieces in sodium hypochlorite to basically bleach the coral and rinse all the organic matter out to get a better scan. And the coral piece that contained the tissue layer, for the corals that didn't record the barium calcium, it seemed to basically wreck the barium calcium signal for that whole piece way outside the tissue layer as well. And I just think, well, maybe it's like a difference in coral skeletal architecture. That's what I sort of came up with. But is it related to species, or is it just a troublesome coral that doesn't want to behave? I don't know.
We bring food in, so we will do that idea. We're going to just have a shorter break. Any thoughts? Does anyone want to give me any feedback on dashboard ideas while we're here?
Do you want me to bring up lens seagrass, or is it going to be a holding?
Yeah, bring up lens.
No thoughts yet? What you want to see up there?
I just had a stylistic thing. As the time series get longer and longer and longer, if we kind of stack them together, if we lose any resolution of the y-axis, which is what we want, the axis changes. You know how to get the y-axis extended.
Are you intending to all be involved in this in the next 10 years? We're just talking about the fact that as we get longer and longer records, how we lose the resolution on y-axis. So
integrated. Instead of having 3 plots, you allow those layers to come onto the plot. So instead of 3 separate ones, you could overlay them.
It's one of the things that I think I really like about natural ideas and do whatever Sorry? As long as the researchers are happy with the way their data's being presented, we can present that anyway, the best way.
Hi people online, we're going to have a shorter break because a few people have to go and we want to get the seagrass talk up and running as fast as possible. So we're going to have a 10-minute break, be back here at 25 past.
Ashim, you'll do the introduction.
Oh, you want me to do that? Okay, all right.
You can hear them.
Okay. Are we all ready, please? So we can get this one before people need to go. I don't want to say names. Alrighty. Okay, thank you everyone. I know it's a short break, but we've had quite a bit to catch up and it's been great to seeing everyone catching up, and I'm really appreciating people coming and talking to me about their ideas for things. So keep it coming. We are now in the afternoon session where we look at seagrass monitoring and coral monitoring, and of course seagrass monitoring is done by Len Mackenzie's team in Trop Water. We've got Catherine still here? Yes. Okay, Catherine's gone. She's missing dinner too. Okay, fair enough. So Len Mackenzie leads the team at Trop Water Seagrass Monitoring 2021-2022.
Thanks, Kay. Okay, so let's start off with why is seagrass so important? Why do we care about and why are we monitoring? Yes, they are an important ecosystem on the Great Barrier Reef, and around about 10% of the Great Barrier Reef World Heritage seafloor has seagrass occurring on it. And if you put that in comparison, corals are around about 8%. So they are pretty significant in terms of the World Heritage Area. Not only are they significant in the World Heritage Area, they're also significant globally. Around about 13% of the world seagrass area is documented within the Great Barrier Reef area. And if we look at just our inshore areas, so that's areas shallower than about 15 metres, you're looking at about 3,500 square kilometres of seagrass. And as we've heard from our previous presenters, that is quite significant when we're talking about what's going on in the Great Barrier Reef. But certainly seagrasses are also important because they are highly diverse, both in terms of species and habitats. They're also highly productive, so they're actually, creating these very critical supporting services upon which so many things depend, and by so contribute important goods and benefits to all resources within the Great Barrier Reef and to human well-being. They also have a high cultural value, and as we become more and more aware of what's going on with seagrasses and issues of climate change, they're a powerful nature-based solution for climate issues. So, and if we look on the bottom there, we can see some of these goods and benefits. So they provide food for dugong and turtle, nursery areas and habitat for fisheries. They do stabilise our coastlines. They also have that, high cultural role and that carbon sequestration, which is so important in their nature-based solutions. So that's just a few of the goods and benefits. There's around about 32 different types of goods and benefits that seagrass provide, and I'm quite sure those within the Great Barrier Reef will provide a lot of those. However, our seagrasses are under pressure from human activities, which are affecting our seagrass ecosystems, both directly and indirectly. Now, those activities that we as humans are doing are being driven by a number of what we refer to as drivers, such as things like economic growth, population growth, and coastal development. And when we look at those sort of threatening activities, we do find that agricultural runoff is one of the greatest threats to seagrass on the Great Barrier Reef, mainly because of the reason it's very diffuse and it's also very chronic. And under these increasing pressures, they really are starting to undermine the capacity of our ecosystems to resist and recover from repeated disturbances. So that relates to the resilience or ecosystem resilience in our system. And there's a couple of main features of resilience for our seagrass ecosystems, and things like resistance. The attributes for that include the abundance of seagrass, the persistence of opportunistic species, genetic diversity, storage reserves, and also spatial extension continuity of those meadows. But also it's important in terms of recovery because that is facilitated by the reproductive output, so things like seed banks, propagule availability, and also by the species composition that are there. And the monitoring of the condition of these ecosystems is really fundamental to our understanding of how these ecosystems respond to the pressures and identify those threats that undermine the system's ability to both resist and recover from disturbances. So, where do we conduct our monitoring? Well, we conduct our monitoring within representative seagrass meadows and habitats in each of the regions across the Great Barrier Reef. We have 35 locations, and of those, 75 sites are being monitored either once or twice a year at least. We're monitoring in estuarine, coastal and reef habitats. It includes both intertidal and shallow subtidal seagrass meadows. And a lot of these meadows are actually dominated by what we refer to as opportunistic species. And our sampling spreads, I don't know if you can make it on that map, but right up in the north, so in Shelbourne Bay, in the Wittity Sea Country, right down into Hervey Bay and in the very northern part of the Great Sandy Strait in the Butchulla Country. So how do we monitor? Well, we do it in an integrated way, and certainly Dan presented that earlier, showing how the program itself integrates, and we do so by collaboration and in partnerships. Now, we do that in several ways. It can be the research providers, some of which we've heard from today, and also NGOs, all getting together and helping us and assisting us in some ways to conduct our monitoring. We also work in with Queensland Parks and Wildlife Service, more specifically with the Reef Joint Management Program, who are helping us a lot with our subtidal monitoring. We also work with community and First Nations groups. In places like Mackay, we actually work very closely with people like the Whitsunday Seagrass volunteers who are out there assessing our intertidal seagrass meadows, and they're assisted by a number of peoples from the First Nations groups there. And we also work with Indigenous rangers.
Checking the seagrass. We have 5 different species of seagrass here. The aim is to see how much seagrass is down the bottom, and we can record it and take photos. There it is. By this screen here, you can see the bottom of the seabed and see if there's any seagrass. And I can see some, so I will take a photo and video it.
So that's how we're getting a lot of our groups also being involved. They collect those subtidal imagery and they send it through to us. And what do we measure and why do we measure it? We're measuring both environmental variables and biological variables. So things like in situ light and temperature, that tells us about the amount of light available for seagrass growth and the impact of things such as elevated seawater temperatures. And in terms of our biological variables, we have things which we measure within a quadrat. So things like the abundance of seagrass, composition of seagrass, the macroalgae cover, epiphyte cover, types of sediment that's there, and also at the overall site, we look at things like seed banks, the numbers of reproductive structures, and we also measure the meadow extent. And that tells us about the condition of the seagrass, the state of the meadow, and the resilience of the seagrass to respond to those impacts from the stresses. Okay, so we've heard earlier from Steve all about those climate pressures. So just to remind us on how things were looking with those pressures over the last 12 months. So tropical cyclones, we do know that there's been an increased frequency of high category cyclones this century. But fortunately, in the last 12 months, we really only had one cyclone, which was a pretty low category 1, that entered the GPR waters. And we did have that tropical cyclone Seth, which was a tropical low, and certainly created some issues when it came back to the Queensland waters just at the bottom of the GBR. Rainfall, reef-wide, was pretty much at typical sort of wet season below or at the long-term average. And in terms of the freshwater discharge, reef-wide, it was pretty similar to the previous period, and it's slightly above the long-term mean. In wet tropics and Mackay Sundays, it was below the long-term median. Cape York, Fitzroy, Burdekin, just above. And in the Burnett Mary, there were significant flow events, particularly those in, bigger than, still not above, not as big as those in 2011 and 2013, but they were certainly significant. So in terms of the measures we are actually collecting as well, so we're collecting in situ light, so our light loggers are within the seagrass canopy, and they're being recorded about 25 of those locations across the Great Barrier Reef. So reef-wide over the last 12 months, the amount of light reaching the top of that sort of seagrass canopy was slightly higher than the long-term average. So if you look at that graph, you'll notice the dashed line is the long-term average, and the solid line through there is what it was for the last 12 months. However, there are a few issues with that data. Cape York was slightly lower. However, we're missing about 30% of the data from there. We only get to visit Cape York once a year, so the chances of failure of those loggers can be high. And in the Fitzroy and the Burnett Mary, they were below the long term. So there are those bottom two graphs. Below the long term, but in the Fitzroy we had some missing data, but that is because in about 2 weeks' time the team will be out there collecting those light loggers. And in the Burnett Mary we actually did lose some loggers with the flood events that occurred, so the whole loggers were gone. But all other regions were generally above that long-term average. In terms of the water temperatures, these loggers are recording, they're within the seagrass canopy, and they're recording temperatures every 30 to 90 minutes. Very soon we've got loggers who will be recording about every 15 minutes. But within the seawater temperatures in that canopy, they were above the long-term average of the majority of the regions across all habitats, even with still stuff missing. And the in situ sea temperatures across the GBR in 21-22 were actually the second highest since the MMP was established, so quite significantly high temperatures. Those high temperatures can also get quite excessive. Elevated temperatures above about 35 degrees Celsius will start to stress the plants. When it gets above about 43 degrees, it results in plant death. And in the wet tropics, Burdick and Mackay Whitsundays, there were more days in the last 12 months where the temperatures were above 40 degrees in the last 6 years. And the hottest day we got was actually at Yule Point, where the temperature got to 45.5 degrees Celsius. And that's the third hottest that we've measured since we started monitoring. Other pressures include things like epiphytes and macroalgae. In terms of our epiphytes, there was a slight increase in our estuarine and reef habitats where they were above the long-term average. So they're the graphs you can see to the left of that panel. However, things like macroalgae, they're always very low in our area, so there's no significant increases there. So how did the actual seagrass look after these pressures? Well, that's our long-term trends in seagrass cover over the life of the program. We do need to be aware that the MMP started in 2005, and we were actually, when we started the MMP, we did adopt several of the legacy sites. So prior to that, there were fewer sites being sampled than there is now. But we have noticed changes over time. You'll see particularly events such as tropical cyclones and multiple years of above average rainfall can certainly reduce the amount of cover of our seagrasses. When we look across the GBR the last 12 months, there's actually been little change, but it still does remain below that 2015-2016 period. So just at the end of that is where we had Tropical Cyclone Debbie went through, and since then it has been struggling to get back to those levels. And if we look at the long term, from about 2005 to 2022, we've noticed that the Fitzroy region is showing a continual decline. There is a long-term decline in Mackay Whitsundays, but that has been abated the last couple of years, so we've seen a little bit of an uptick there. If we look at the habitats in which we've been monitoring, estuarine and coastal habitats, those panels to the left, they both declined in the last 12 months, while reef habitats actually increased or remained unchanged. So those really near shore habitats were ones which are showing declines. And if you can make that out, that's where we're actually looking at those habitats across those regions. Places like the Mackay Whitsundays improved or remained stable in all its habitats except the subtidal. And abundance declined in all habitats in those southernmost regions. So Within the Fitzroy and Burnett Mary, which are the dashed lines, both those regions decreased in all habitats in the last 12 months and have done so in the last couple of years. So when we look at how to score our indicators of abundance, we do that against our guideline values and the Great Barrier Reef wide, where we're looking at relative to the guidelines, has remained above the long-term average over the last 12 months, and it's putting it essentially in a moderate state. However, the wet tropics and Burdekin increase, while places like Fitzroy and Burnett Mary continued to decrease. If we look at things like meadow area, so this is where we look at the extent of it, the seagrass around our monitoring sites, and we generally find that in the wet season it's a bit lower, so the bluer bars are the wet periods, wet season, and the green is our dry season, so wet season always get a bit of a decrease. So it can also be significantly influenced by disturbance events. So where we see big drops is where we've had some of those cyclonic events or periods of flooding. In 2021-22, the meadow extent continued to improve. That's really where the meadows had been quite fragmented, but in the last 12 months, they had become a little bit more cohesive. If we look at the composition of species within those meadows, because species is also helping us with things like resistance and recovery, most of those species display those colonising features when there's stages of disturbance. So if you get a loss of seagrass or some damaging activity, your seagrass meadows can change from opportunistic species to more pioneering species. So what we'd like to see is not so much of the pioneering species. As you can see, when the pioneering species are high, really highlights those times like in 2011 and 2012 when we had those big events. So the good news was in the last 12 months, the species composition has improved with the proportion of colonising ones at or below the long-term average. Looking at its reproductive status, so how well are they flowering and producing fruits? Reproductive effort remained unchanged and below the GBR long-term average across most habitats. So right across the GBR, it's actually pretty poor. And when we look at seed banks, because we've got fairly low reproduction, we've had fairly low reproduction the last couple of years, our seed banks, although they've been improving in some places like the coastal intertidal meadows, the other habitats we've seen very little change. So using information such as the abundant state, the species composition, and the reproductive effort and the history of the reproductive effort, because what we see today can be the product of a couple of years in terms of reproductive history, we've developed the resilience indicator, and that indicator looks at the balance of species and the reproductive effort. So it looks at how much of the seagrass is colonising species, and then looking at that to see whether it's low resistance or high resistance in terms of its abundance and whether it's being reproductive or not. We then score that to then look at our resilience indicator, and we've noticed there is a slight improvement after declines of 2016 to 2020. However, it still remains below that long-term average. Unfortunately, once again, if you can pick it out, those declines have continued. If you look at the far right, the dashed lines on the lower part of the portion are the Fitzroy and Burnett Mary, which have also declined. So we've seen declines in those regions in both the seagrass abundance and seagrass resilience. So when we put those indicators together, we actually get our condition for seagrass across the GBR. So both those indicators were improving in the last 12 months. There was a slight decline in the abundance indicator. However, both those indicators are within a moderate state, and the overall state for the GBR in 2021-22 is moderate. Even though it's moderate, it still is below the long-term average. And if we look at the individual regions and their conditions, Once again, of concern are those, the southernmost, the Fitzroy and Burnett, which have continued to decrease. So over the last 2 to 3 years, they have been decreasing. So if we were then to look at overall in terms of our seagrass and summarise what happened in the last 12 months, we'll see that apart from higher than average within meadow seawater temperatures, the climatic and environmental pressures were generally low. An exception of that is in the very south of the GBR. Reef-wide inshore seagrass condition marginally improved. But yes, we did see those declines in the southern regions as a result of localised disturbances and extreme events such as flooding. So once again, as I was sort of real warning last year, our findings are continuing to suggest that seagrass ecosystems in the Fitzroy and Burnett Mary regions remain highly vulnerable to any adverse or severe disturbances in the immediate future. And as we're coming into a period now where we're expecting probably more cyclones and more floods, that's not good to hear. So, what does that mean and why is it important to keep monitoring? Well, we need to remember that monitoring provides us with the evidence base for management actions. It helps us to identify when interventions may be needed and also to evaluate the success of those management actions or interventions. So if we take a look at these 3 plots, for example, the plot on the left is showing seagrass condition over time. It's been hit by acute disturbances, but it's bounced back to essentially what it was. So we would say in that situation that seagrass ecosystem is in a fairly resilient state. It is highly connected to its adjacent systems and all the animals and everything is pretty much in balance. The one in the middle, when it's being hit with these multiple disturbances, it hasn't yet recovered to what it used to be, which is pretty much what we're looking at for much of the GBR at the moment. In that sort of situation, it's definitely not in its high resilient state. It's a damaged ecosystem. And the final one, when you have a damaged ecosystem and you hit it again, it could actually push it to a collapsed system where we lose our seagrass. We lose a lot of those contributions that seagrass make to the environment. Now, when we look at each of those outcomes, there's 3, I suppose, different approaches we can take in terms of what management can do. That's what monitoring can help us identify. In the first one, a resilient seagrass meadow, this is where an existing seagrass ecosystem is in a good state. So really things like conservation and preservation is the best we can really do. In the middle one, where we're seeing a damaged seagrass ecosystem and its components, we need to consider things like repairing and even enhancing as pressures get higher and higher as we continue into the future. Or when we've got a collapsed or lost ecosystem, we may have to look at things like restoring and possible creation of seagrass habitats. So when you look at those 3 different approaches, if you look at the first one, not very exciting to the general public. It's not particularly engaging. It is variable cost to deal with it. And it also requires a long-term investment. And because we're talking about conservation, that's about sustainable use, it's going to have some stakeholder challenges in there as well. But you get big ecological benefits from that, and this is something that works quite successfully over the large scale. If we go to the other extreme, restoring or creating, that at the moment seems much more exciting. People are much more engaged by that. It is high cost, and what we need to realise is all the lessons we're learning from overseas. You're talking about short-term goals. Particularly in our tropical seagrass ecosystems, it has a high failure rate. And its ecological benefits are questionable. I say that because when a system has collapsed, it's lost all its feedbacks, it's lost all its components. Just planting seagrass there is not going to instantly bring it back. And it's the issue of scale. Things like restorations work quite good at little scales, maybe the size of this room if you're lucky, but anything bigger than that, very few examples where it has even some level of success. So what we need to think about is more, let's not wait till it collapses, let's do something earlier. And yes, to repair and enhance, it is going to be a variable cost because we're dealing with different situations. And it can have variable temporal investment because in some it doesn't happen across the whole region. It may be in one region 1 year, different region another year. The thing is, when you discuss this with people, there is a lot of stakeholder positivity. They do think it's a good idea. It sounds quite exciting and engaging because it involves elements of what the restoration and creation is doing. It also has big ecological benefits, and you can do it at multiple scales. So, you know, if we're thinking about what to do with these resources, when we're seeing them being damaged, I would not be waiting much longer before we actually step in. Don't wait till they collapse. So I suppose one of my last slides is, I suppose it's about a bit of a call to action. I think it's time we started being prepared. You know, last century I was a Boy Scout and that was our motto, be prepared. I think we need to do that for the Great Barrier Reef. And I think we need to look at building and enhancing resilience in our systems. And there are things we can do. In the way we manage for resilience, we could identify and protect high value seagrass areas or protect areas which are favourable for seagrass colonisation. Support ecological linkages, you know, maintain those trophic linkages. We can identify and protect key species that sustain seagrass resilience. Things like sharks are actually quite important in these systems. Identify and incorporate genotypes of seagrass which are resistant to environmental stresses. We're thinking about doing it for corals. We should be doing it for seagrass as well. And we need to identify and protect important cultural, social, and economic values. We need to recognise those values. We have a huge failing on the Great Barrier Reef actually recognising what those values are, let alone being able to protect them. We can start delivering on-ground actions. We can improve compliance and spatial planning. You know, simple things in a small scales. It could be using seagrass-friendly moorings or designated trim your motor and go slow areas. There are things we can do. We could develop guidelines and policies that enable seagrass interventions. At the moment, we don't have we have barely any guidelines available. What guidelines we do have for seagrass come from temperate systems, totally different species, and really not applicable to what we're dealing with. We need to start conducting some, small scale, looking at things like seeds, putting seeds out and doing those trials and at appropriately identified locations. We do know what lessons we've learned from overseas is taking a plant from one area and just sticking it in a bare area of another doesn't work. That is where you're wasting money. We need to be a bit more smart how we do this. One of the things we can do is establish what we refer to as seagrass resilience centres. So we've been discussing these and seeing if the First Nations groups are interested in helping with this. And this is where we can cultivate seagrass propagules, where we can conduct underpinning research. It can provide issues such as ecotourism, and we can use that to provide a ready response. So if you have those along the Queensland coastline, they'll be developed in areas which are applicable to the seagrass ecosystems in that area. And we can also expand and enhance our monitoring, include other things like genetic diversity, some of those things we're missing. And there's always that need for continual improvement, things like to eliminate those critical knowledge gaps. We know very little about seagrass reproduction, we really do. We need to enhance new and embrace new technologies. The way we map seagrasses, there are better ways we can do it now. It's not being done enough, but we know we've published this work. You can do it much better than we have. We can also implement more effective communication and awareness raising initiatives. One thing we lack with seagrass ecosystems is visibility. The general public doesn't know what it is. They just think it's a weed. They don't understand the difference of the difference between a seagrass and a macroalgae. They don't understand about the immense important contributions that seagrass make to our lives and to our coastal areas. And an important thing is also to foster partnerships. We really need to work on that, support public participation and to empower people to get involved. I think if we can do some of those things, they're immediate actions we can start working on. And I think it is a call to action because we can't wait much longer for this. Some of these systems are going to start collapsing if we don't do anything. And with that, I suppose if you want to learn more about the MMP and the results, yes, at the moment you can go to the Gaboompa one where you'll find our reports and hopefully the dashboard isn't too far away. Or you can go on to the Seagrass Watch website, and if you go on to that, you can actually go down to individual sites that are being monitored and explore the data that's being collected there. They're interactive graphs that will let you know what the seagrass is like, what condition it's in, what the macroalgae is like, all those sorts of things. And I'll finish there.
Thanks, Lynn. I know this is going to be I shouldn't say it because we all know this, but the protection and conservation, addressing the reasons why the seagrass are declining, should not be forgotten in the kind of middle bit where we're doing the kind of interventions. That's true for coral, and that's true for seagrass. We all know that, but I couldn't help myself. Thanks.
Yeah, I suppose I didn't want to imply that it wasn't there. I mean, that is something that should be there regardless. But the problem is people are rushing to restoration. Restoration is the buzzword. Restoration is where they're throwing money at people. And in terms of seagrass, they're talking about blue carbon. We don't have blue carbon credits in Australia. It's like, and who owns it? I mean, I know there's debates going on. Does the Queensland public own it? Do the traditional owners own it? I mean, it's not a simple panacea to just say, let's all protect it because of blue carbon. This blue carbon blindness is causing big problems even across the Pacific. So.
Do you want to go back to that slide with the three options?
Thank you.
I don't know about options, but there's certainly
Options. Possibilities. Do you want to just see if you can run through a couple of ideas between the difference between repair and enhance and restore?
Okay, so usually when the definition of restoration is a confusing one because some people believe restoration is both repairing I suppose if you think of it like a house, when someone says, I want to restore my house, the house hasn't completely collapsed. It's still there, you just want to restore back to what it used to be. However, most in environmental sciences, when they talk about the restoring, it is really about when you've got a fully lost or collapsed ecosystem. So it's not there, it used to once be there, and I want to get it back to how it used to be, is usually what restoration talks about. Creation, yeah, that can be where it works in two ways. You've lost seagrass. So the feedbacks, the things that seagrass provide, like stabilising sediments, or your sediments have now become resuspended, your water's become turbid, seagrass not going to grow there because there's not enough light. So you're going to have to create a better environment. So you might need to put in something to stabilise the sediment, something to baffle the waves, to make it calmer and settle it so seagrass can start to grow. Creation also involves where you look at areas where a model may indicate it has all the correct factors and parameters for seagrass to grow, but seagrass isn't there. Maybe it's not there because the propagules have never got there. So you can create a seagrass habitat by just putting the propagules there. So that's how that works. Repairing and enhance is really looking at your ecosystems and giving it a boost. So, you see your ecosystem, you see your seagrass meadows starting to decline, it's becoming fragmented. Maybe just putting in some seeds and boosting it along, giving it some, seeds when they grow, they're creating the environment, they're putting all those feedbacks in place, which is very different to just sticking in a plant. So, improving things like seeds will just give it a boost because it's probably at a state where it's highly stressed and it may not be flowering and producing seeds. So you can give it a bit of a boost. And enhance means think about getting it back to better than it was because the pressures are just going to increase with climate change. So that's where you might need to be realistic about your seagrass species. Some of our species may start heading south. So no point planting a very more subtropical temperate species in a tropical area. So you may need to think about, okay, we've lost my Zostra species from here, but I can replace that with something like Hologila uninervis. It'll give you the same contributions, the same benefits, the same supporting services, but yeah, it's a species that will be able to tolerate, the levels of increasing heat and variation, or levels of disturbance better than what maybe the Zostra do. So they're things you need to think about.
Does that mean we should be considering possibly species that are currently not growing in the Great Barrier Reef?
No. I mean, the species we have, what's in the Great Barrier Reef are the same species in the Indo-Pacific. There are other species around which really I would not like to encourage to come from the Middle East or from the Caribbean. But the species we have mix from across the Indo-Pacific. So, as times change, we're going to see those equatorial species become more prolific in the Great Barrier Reef. Instead of, we have Inhalus acoroides, which is a big, robust species around the equator. I think the most southern it's ever been found was on Magnetic Island. I mean, we know it can grow down here. It just doesn't proliferate like it does in other areas. So it might be one that starts creeping south, those sorts of things. Even in south of the Whitsundays, some of our reef species don't go past Whitsundays. So thalassias and thalassodendrons don't go past there. So they might start heading south. So, yeah.
I think one of the things that came to me when we're talking about that, and hence my question, is our use of language again, and making sure that we're using the same definitions for the language that we use. And what you described to me is I'm questioning is perhaps not quite the same definition that we're actually working. I'm getting nods over there from our planning section. So it's really interesting. I really enjoyed that presentation. Anyone with questions? Brilliant.
I'm not sure what that means.
So our last talk of the day, you're from Angus. Our coral expert. It's been actually part of the program since the beginning as well, right?
Yes.
Yes, cool. Talking about the state of inshore corals.
Right. I might take a moment to get the idea of Len in a scout uniform out of my mind, but I'll try. Great talk, Len. So I'm going to cover off on the coral state they're in at the moment on behalf of myself and Cassie and Johnston, who are in the crowd. So I'll just jump straight in. Maybe, not that one. Yes. We've seen this slide and it's a consistent theme across the program, but really what we're looking at is that there's cumulative pressures influencing all the inshore habitats, and there's the big climate-related pressures such as cyclones and bleaching events, but then there's our socio-economic use of the environment, and that causes the land runoff and the issues, maybe some direct impact also. And the idea of the monitoring program is really to assess what's going on in the inshore reefs, seagrasses, water quality, to feed that back up to make sure that if there's a need, then what we're doing on the land and how we're managing the system can be altered. Again, following on a bit from what Len showed, the resilience of coral reefs is really a sort of a two-phase thing. It's their resistance and recovery potential. So we know that they're dynamic systems. They get impacted by chronic acute events such as cyclones or bleaching events. But then if the chronic pressures are fairly light, they can recover. And so on the long term, we get a sort of stable system. The concern with water quality in particular, but also increasing acute pressures such as climate change, heating, is that we get a decline, we don't get such a good recovery rate, and we can get this ratcheting down, which sort of follows on from some of the options that Len brought forward, that we might be triggers for different options of management. Again, where we monitor the reefs in 4 NRM regions only. We don't go up to the Cape, primarily because we're working in these inshore reefs and we're diving operated at the moment, and that's not really accessible to us up there. So we go down from around the Keppel group down south, through the Whitsunday group, and then coastal reefs between Townsville and Snapper Island, just north of Cairns. Sorry, this is going to be terrible. The way we monitor, we access all these sites in a small boat, just to take advantage of good weather, so we can both be comfortable but also see what we're doing, because there's a lot of resuspension obviously with wind in these inshore environments. We have 3 methods that we use to monitor. When we're rolling out our tape measures, we have permanent transects so that we're on the exact same location every year, which is really important for precise measurements of change. But while we're swimming out this tape, we're looking for what's killing the coral. In this instance, we'd be recording a whole lot of bleaching, but there might be crown of thorn starfish, there might be all broken up from a recent cyclone, etc. Once that tape's down, we swim back along these transects, taking photos every 50 centimetres. This is Johnson in action. And from this, we build up a % cover of major benthic components, the corals, what types of corals they are, the algae, etc. And then finally, coming back along the transects, we come along and we count the juvenile corals to make sure that recruitment process is functional. Again, to make sense of the state of the reefs, we need to understand the disturbance history that we've seen. This is just a brief sort of the last decade or so of cyclone tracks that have impacted the reef. As we've seen, the last couple of years have been pretty light. Prior to that, we had Cyclone Debbie running through the Whitsundays, which was a big event, and we'll talk about that again later. And then prior to that, there was quite a lot of cyclone activities, and not only was that relating to direct damage, but there was a lot of rainfall in that period too. The other thing that's really been impacting corals is bleaching events. You'll all be fully aware of the impact that they have. This is just the last 5 years. There was also 2016 and 17 were both well above average temperatures on the reef and impacted some of our sites. Just to interpret this plot, once you're getting up in the reds, then there's a very high chance that you'll have bleaching-related mortality. And so you can see that in 2020, for the inshore sites, they sort of went from Townsville, followed the coast down and right to the south end of down into the Fitzroy region. But this year's bleaching event was really located very close to the coast and around Townsville in those red colours. And again, we've seen this plot before. I've just narrowed it down to the places that we monitor the corals, and the take-home point from this is that very wet period in 2008, 2012, because we did see a decline in coral condition associated with those inputs. So from those transects where we swim along and decide what's killing the coral, then that allows us to look at the loss of coral and assign a cause to it. And what we can see in this plot is what the sort of causes for coral loss on our sites over the years. And this is the difference between the coral cover that we expect if we allowed it to grow from when we saw it last year to what we actually observed. And so these big years of disturbance, on average, we lost sort of 10% of coral cover on reefs during Cyclone Yasi, for instance. But the big events are all cyclone related. Cyclone Debbie obviously hit the Whitsundays, but there was also bleaching in other areas in that year. Cyclone Larry hit the wet tropics, but that bleaching event was down in the Keppels in that year. So when we look at the sum of all these different disturbance events, we can see that storms or cyclones are still responsible for the majority of the coral lost. In over the period of these surveys, but we've got crown of thorns running through in places. We've had outbreaks of disease. We've had direct influence of flood events, particularly down in the Keppels, and we've had bleaching losses. So looking at coral cover itself, just as the most tangible of the indicators that we monitor, and this is the long-term trend since we started back in 2005, and you can see that looks like a ratcheting down. The colours here of the report card colours, I'll get to them in a moment, but so the overall condition, we can see that coral cover has had some big impacts with those big bleaching and cyclone events, and the overall condition over the sort of 18 years that we've been monitoring is for a decline. But that's different at the different regions. They're the underlying coloured lines there. And so we can see the wet tropics has actually gone up since we've started monitoring over the 18-year period and is in good condition. The Burdekin is in moderate condition. Mackay Whitsunday has gone down since the beginning of the surveys, and Fitzroy has also gone down, and it's really, that ratcheting down is almost entirely due to the story in the current state of coral cover in the Whitsundays. And now I'll just take my time to explain these colours. These are the report card colours, because the MMP was designed to feed information up into the reef report card. So these are the report card grades, whereas the dark green would be grade A, very good condition. B is a lighter green, moderate, so that's just the C grade. And then we go down to the orange and red for poor and very poor, and D and E. What I'm going to do now is for each of the 6 sub-regions, because there's 3 sub-regions in the wet tropics and then the 3 regions to the south, I'm going to present 3 plots. This one and then the next 2. So for those that need to count down your endurance, that's 18. And the first plot will just look at the long-term trend and some of the major impacts that have occurred. Then I'll compare the current condition to the initial condition in the monitoring, and then just focus in on the individual reefs and just have a quick view of which reefs are in good condition and which reefs aren't in the regions. So what we can see straight away in this region is that there was this period where we had some disease followed by crown of thorns outbreaks, and then a storm which really pulled the coral down in the Barren Daintree region. Since then, we've had a bit of a recovery, but there was a flood event. There was also some storm damage associated with that and ongoing crown of thorns. But in general, we've seen this recovery just with those little punctuations from slight disturbances. When we look at the condition now compared to later, so on the on the left-hand side, is what we saw in the beginning, and the reason the dates changed there is that macroalgae and coral could be, and juvenile density, and maybe not juvenile density, that might have been the next year, could be determined at the beginning in 2005, but the composition and the coral change scores, we needed a few years, so they came online a little later. In 2008 is sort of the most extreme in the data set. Most reefs came online in 2006 or 7. But really what we're seeing here is that the macroalgae is one of the clear changes. So we've had more macroalgae coming up. It's still in moderate condition, but it's come down from being in good condition, or very good condition. So it's just at a couple of reefs. Those error bars, which extend all the way to the outside of the circles, tell you that there's high variability among sites in that condition. One of the things that has occurred, obviously, is coral cover is now higher than it was at the beginning, which is great to see, and it's been growing at a good rate, which is what the coral change indicator means, is how fast the coral's growing. But what we've seen is a drop in composition. So we've lost some of the sensitive species in lieu of some of the tougher species. So we've got lower acropora cover there now, and proportionally more parietes is mostly that story. And then juvenile densities are reasonably low, but haven't really changed. when we look at the individual reefs in this region, we can see that Low Isles, surveyed offshore there by the long-term monitoring program, is in good condition as we come closer into Snapper Island. And then when there's paired dots, that's a 2 metres on the left and 5 metre sites on the right, so it's often quite different over those quite small difference in depth. So the only site there that's pulling the scores down is Snapper North at 2 metres, where there's very high incidence, a very high cover of macroalgae that's persisted there for a number of years now, and that's resulting in low juvenile densities. And the composition of that community has changed to away from a dominance of Acropora. But it's actually quite localised too, so it's not at all the sites there. On the left there, that's the kind of macroalgae we're talking about. One thing that's good about that now is that there's those pinkish bits which are coralline algae. In the last few years, that's been really mucky turf algae with sediment in it, so it's cleaned up a fair bit. So we're hoping that now that might kick on, and certainly other areas in that shallow site are getting coral back on them quite nicely. That's three. into the Johnson-Russell Mulgrave. The big impact here, well, the first impact was Cyclone Larry, which hit and that brought it down to, so it was still in good condition though in 2006 when this time series starts. 2011 Cyclone Yasi created quite a bit of impact, but since then we've had crown of thorns starfish, and this is the only sub-region where this has occurred on the inshore, where the crown of thorns have been an issue, and they've really persisted right through. They're still there now at one of the reefs, and then there's been some bleaching involved in that as well. But even with the crown of thorns through there, you can see that and this is sort of just this is an example of what we saw at our worst impacted site. On the left, that's straight after Cyclone Yasi. There wasn't much coral there at all. In the middle there, this is just a couple of years ago, the coral had grown back, and that's the star picket is. So that's recovered really well, but at that time there was quite a lot of juvenile crown of thorns in the bottom of those stags, and then 2022, that's what it looks like now, and so they have been eradicated from there pretty well by the crown of thorns control program. But for this site it was a bit late, but other areas of the reef they've certainly helped. And then the only thing that there's a bit of a dip now, and that's really due to some macroalgae at a couple of reefs. And here it's not the big brown fleshy macroalgae that have really created phase shifts on other reefs. It's red algae that get in amongst the sort of fine structured parietes and that really do form a blanket that stops any coral recruitment. Again, looking at the changes, I'll try and be fairly brief on this. That macroalgae has come up on a couple of reefs. Coral cover is above what it's been in the past. At the beginning, cover has been growing quite well. We're not impacted by crown of thorns or bleaching or cyclones, so that's good, and the composition's on track to what it was before, so we haven't lost any of those sensitive or fast-growing species. And again, the juveniles are fairly low. And just looking at the individual reefs, the north, or what we call Fitzroy West, is in good condition. The 3 dots there is because the LTMP, long-term monitoring at AIMS, have a site there as well as us. Everywhere else they're in moderate condition, except for in the shallows at the Franklin group where they're in good condition. And the crown of thorns didn't really get up into there. There are still crown of thorns at High Island in outbreak conditions, but elsewhere in this region, there's been a lot of crown of thorns removed from Fitzroy and the Franklin group, and that's really sort of helped keep the corals going there. And this is just a picture to show what those green reefs are looking like up there on the north side of Fitzroy. It's pretty well full of hard and soft corals. Into the Tully Herbert, those same two cyclones, Cyclone Larry, Cyclone Yasi, they went straight over the top of this region, lost a lot of coral from them, but we've seen some really strong recovery. I've sort of got that purple line there for the coral cover recovery in purple, bolded, just to demonstrate what's going on. This is one of the sites that was most impacted on the north side of Dunk Island. This is the same piece of reef. That tape measure is attached to the Rio rod in the left-hand side, so it's just out of picture. And those big plate corals are growing on what was just pretty much a bare rock, and all filled in around the bottom there are those staghorn corals. So it's looking, remarkably different over a decade. And again, we can see this. The composition is still pretty good there. So we've got those, which you can see from that photo, those fast-growing acroporas have come back in. Coral cover's pretty much on par with what it was, a little bit higher. And the rate of change has been good. There's lots of juvenile corals, but it's a little bit of a double-edged sword here, because they're little turbine areas which are coming in their thousands that don't really survive particularly well. But macroalgae is a bit of a kicker in this region, right down there in that bay outside the Tully. And when we look at it, we've sort of in moderate to good condition across all these reefs. There is some allowance in this, the way we score reefs, for the actual underlying location along water quality gradient. So that good condition at Badara at 5 metres is not the same sort of coral as at the North Barnard 2 metres, where you've got flourishing acropora corals. You've got a situation where there's no macroalgae because it's actually too dark, but there is lots of juvenile corals there, and the coral community hasn't changed, but then it's already selected for really marginal habitat. So you need to take this one with a bit of a grain of salt in these sorts of situations. What is driving the 2 metre sites down, and we saw it in that previous plot, is that there's a lot of macroalgae in the shallow sites still at those 3 southern reefs, and they're sort of pulling the scores down a little bit, but otherwise things are looking pretty good. In the Burdekin, Cyclone Yasi, yet again, it was a really damaging system. And again, coral has recovered, but nowhere near as fast as it did just to the north. But what we've seen since then is those bleaching events. We've sort of had, 2017, 16, 17, 20, and then 22, we saw bleaching in this region. This is in 2020 at Jeffrey Bay. A lot of that coral did recover, but not all of it. So. And again, where we didn't get that bleaching, remember back in the bleaching slide I showed you, it was very coastal. Offshore, it outside the palms, it really didn't get bleached at all, and it's actually recovered. This is again since Cyclone Yasi, huge increase in acropora cover there. The exact same picket in those 2 photos. And again, they're just to reiterate that was that bleaching really coastal. Again, looking through the Burdekin region, coral cover is kind of slightly higher than it was at the beginning of the surveys. It's been changing at a rate that we expect. The composition is good, and but macroalgae, again, is one of the things that's pulling that down and probably also influencing the low juvenile scores there. When we look at the reefs, you can really see the impact, how much better the more offshore sites are than the more inshore sites, with sort of poor and very poor condition on some of those inshore reefs. And that's really, at all of those sites, we've got high macroalgae cover and low juveniles. So this is sort of Jeffrey Bay when we were there this year. There is some nice little patches of coral, but there's a lot of this heavy sargassum which has really shifted that reef ever since we've been surveying it into a macroalgal dominance. Into the Mackay Whitsundays, they were tracking along. We just had a little blip from Cyclone Louis, but But then the big impact of Cyclone Debbie, that looks like it spans 3 years, but it's just that it took 3 years to get all the sites resurveyed after the cyclone. So that's actually just a vertical drop in condition. So but the thing, it was in good condition just prior to the cyclone. But one of the things to note here is the influence of sort of the combined influence of disease and chronic is getting up towards 30% of the coral loss, even with that big impact of the cyclone. And that's just demonstrating, the underlying environmental pressures that are making the corals grow slowly or knocking them off. Again, pre and post cyclone lack of recovery in this instance. 2016, 2017 there was nothing there, and there's still just macroalgae at that site at Double Cone. And what we can see now is that have I been doing this, talking to this slide, like a slide ahead of that slide? Okay. Yeah, so here the macroalgae is the one that's of most concern. I mean, we can accept that the cyclone knocked down coral cover and it's now low, but that macroalgae and that slow cover change that's, we've got macroalgae now, we've always had slow cover change. The composition, we've lost a lot of those fast-growing species, which you can expect after a storm. And the juveniles aren't in too bad a condition, and in fact they've really increased in the last year, which is a positive. The impacts, most of those red reefs were impacted by the cyclone, although Pine Island has been coming down for a little while. Dent Island is an interesting one because that got impacted by the cyclone just a little bit, broke the corals up, but it really didn't kill at all. But then over the next 3 or 4 years, disease has gone through and taken out all the Acropora there. So there's something else going on there. It's unusual to have lost all that coral amongst the entire suite of our data for no apparent reason. So there was quite strong disease signal there. Chute Harbour, just sitting there, managed to miss any impact and is just flourishing. And one thing that has occurred, and the difference at Daydream there from very poor in the shallows to poor in the depths, these are only literally from here to the speaker apart. Up in the shallows, heaps of macroalgae. Down in the depths, a lot of that macroalgae isn't there. This was very highly covered in sediment for a number of years after the cyclone, which is now cleared out, and we're getting really high numbers of juveniles, which has boosted that score up. There's still not really any coral cover there, but there's heaps of juveniles, so it's good. Finally, the Fitzroy. This one had a long demise. There was bleaching in 2006. There was a couple of flood events which outright killed the coral at some of the exposed reefs. There was disease associated with all that extra nutrient and sediment that was in the bay for a number of years, and then sort of slow growth and a couple of storms really put it all down into a very poor condition. But you can see that purple line there. The coral cover has really been cranking up in recent years. But it's a bit of a two-phase recovery that's been going on, and I'll just get to that in a minute, because these macroalgae in this area is what's really a big issue. It's, compared to when we first started, there's just heaps more big brown macroalgae at most reefs. It's really only at Daydream, at Barren Island, the most offshore reef, that we don't have a lot of macroalgae. And so what's occurred there is that we've lost the Acropora dominance on a couple of reefs, or reduced the amount of it. Coral cover is still well below what it was when we started. Corals are growing at a reasonable rate. Juvenile densities are very low under these macroalgae beds, and you can see it's all those poor reefs there, poor and very poor, all have high macroalgae cover, and it's it's looking like this. It's a bit hard to see really, but there's in amongst that staghorn coral is all the Bophora algae, which just completely precludes the ability for corals to settle. But then along the bottom there, that more vertical algae, that's the big sargassums, and once they get in, they are really persistent for a long time. So we're seeing them coming in here and at a couple of other spots, and also a little bit in the Whitsundays. So they're, these are the ones that you might be able to weed out potentially, because I've never seen them disappear once they're on a reef. They make very good persistent stands. So this is a bit hard. Kay hates this because she's not colourblind. There's a real two-phase recovery thing going on the inshore reefs. And it's to do with along water quality gradients, where the chlorophyll levels are reasonably low, we're getting high coral cover relative to on the more nutrient-enriched reefs. And on the flip side, we're getting more algae on the other reefs. So where we get beyond that algal issue, then the corals are growing just fine, covering really well. But where we're down in the high macroalgae proportions, in the higher end of the chlorophyll gradient, that's when we're really struggling. And I've only got the 2 metre depth there for the algae because it falls apart a bit at 5 metres, because once we get into those high nutrient levels, it's also too dark for the macroalgae. So at 5 metres, there's no story, but there is in the coral cover. So we haven't got a shift to macroalgae, but we're not getting the coral recovering either. So, and then finally, in the long term, if we take the kind of DIN loads that are coming down from the rivers, and this is really mirrored by just simply discharge, they're not strong, but if we look at all the changes in the coral index score, so the summary of those 5 from one year to the next, after excluding all the observations where they're impacted by an acute event like a cyclone or crown of thorns feeding, or a bleaching event, then the change in that index, so the rate that those reefs are recovering, tends to be higher when there's less discharge or DIN coming in from the catchments than when there's high loads. And they tend to be more negative. So if you're below that line, then the index is going down. If you're above that line, the index is going up. It's obviously very variable because there's all sorts of things going on, and there's a whole range of different communities here, 35 different reefs, but there is that tendency. So it sort of really does reinforce the idea that the corals do respond to the water quality. So in summary, the condition of these reefs is highly variable, but it's, over the whole system, it's been relatively stable over the last year. And it's not too far off what was observed at the beginning of the program. It's really only in that Whitsundays area that it's really down, and also in the Fitzroy, because the coral index didn't get scored until 2006, and which was the year after it got hit by the bleaching event. Cyclones are still a big issue, but it's really, how we're recovering from those cyclones that is the kicker for some of these reefs. The crown of thorns populations, they did impact the Russell Mulgrave reefs. The reefs are in good condition now, or moderate to good condition, but they would have been far, far better if the crown of thorns hadn't been there for the last 6 or 7 years. The Mackay Whitsunday reefs, they are low, but as I was saying, that strong recruitment where the macroalgae aren't is a really promising sign. Just the concern is sort of how persistent those macroalgal communities become. At Pine Island, we do have sargassum there, and we've had that since the program began, and that's never really changed. So, we really don't want to see that getting hold in anywhere else. And so ultimately the resilience of these inshore reefs declines during periods of high catchment input, and with increased exposure to poor water quality. But it really is, even in the inshore reefs, we are only talking about those very near coastal reefs that are showing that really strong signal, there's certainly reason to be fairly buoyant about the condition of the reefs sort of on the outside of the islands that we've been monitoring. So that's it. You can find, as we've seen, the reports on the Marine Park website, and then hopefully soon the Reef Knowledge System on the dashboard. You can also, ideally, once that's up and running, you'll be able to link straight out to the AIMS website where we have individual reefs, and you can look at the composition of the communities and see photos and trends in time of all of the indicators on those that we monitor. And eventually this will feed into the reef report cards. Thank you.
Any questions?
Christina.
Water quality question for you.
Oh, okay.
Just looking at your photos, I think particularly it was around the wet tropics region, the water quality in many of them seemed bright green. And I'm guessing you're not out there in floods. Is that?
No, well, not usually, but as Steve mentioned, it was a very late, there was a bit of a late rain event this year, and we were right in the middle of it.
I was wondering if that always looks like that.
No. It was really hard to get current photos this year because it was so dark. Yeah. I think it was that time when it was, like minimum of, it was like below 10s, and we were holed up in Mission Beach in the caravan park freezing. Yeah.
I was wondering, do you have much of an idea of the recovery back to good in for reefs that are and are not exposed to poor water quality?
Yes, so that really is that macroalgae story. So the macroalgae are the reefs exposed to poor water quality, and the other reefs, in those regions. So when we were seeing the green dots on the reefs furthest from the rivers in every region, that's that story. So even though they've all kind of been exposed to more or less within regions the same disturbance events, inshore they're, the ones closer to the coast, which is poorer water quality, have not recovered or, are in a worse state.
Do you know how long
Well, it's a bit hard to say. So, like, Jeffrey Bay has been exposed to poor water quality, and it really hasn't changed in the 18 years we've been monitoring it. It's been stuck at a pretty constant level. It tries to recover, but the disturbance history is enough just to keep it where it is. Whereas those other reefs that I showed photos of since Cyclone Yasi, so that's 11 years ago, and they're looking great. So, but yeah, others, we don't have an endpoint to that.
Just continuing on that same question, do you have any comments on the shoot harbour sites?
Yeah, well, the corals can and do survive in really poor water quality, and they need to be disturbed, and if they haven't been disturbed for a long time, they'll eventually win. But so those sites have probably just not had a disturbance for eons, and you can see why, because they're in a kind of bay surrounded by islands, so there's never going to be cyclone waves there, and there's no rivers putting fresh water directly onto them, and in fact the rivers in that whole region aren't particularly large flow, so they've just been lucky. You know?
I guess it's that cumulative impacts.
Richard.
Okay, thanks. Havana North, there was a site that was green, so it was good.
Yeah.
Just to the south was a site that was red, so that was very poor.
Yep.
So just wondering what the story was there in terms of the, what the indicators are showing there.
Let me get this right. So the southern site that was red is at 2 metres depth, and that got pretty heavily bleached, and then it recovered quite well since Cyclone Yasi. Had a lot of Acropora grew back, but they died off with the bleaching events. So they were it was Acropora pulchra, which was a very sensitive coral to bleaching. So that died through, and then we had disease run through there, and then macroalgae come in. That site on the north side is the LTMP site, and that was written up as a phase shift site, and it stayed in macroalgal dominance since before this program started. So it was pretty bad for a long time, but it's just started to lose some macroalgae in the last survey and get some juveniles in there. It still hasn't got a lot of coral, but because it's low coral cover and it's starting to recover, then the coral change score is quite good. So it's starting to kick on. But it's a depth thing.
Just an observation with Maggie Island. We think that some of the nutrients there are actually coming from the island and discharges from the island. Is it a similar situation in the Whitsundays where you've got tourism development potentially discharging to near where the corals are?
At Dent, quite possibly. They just developed a golf course on Dent Island and the access for the barge is just a few hundred metres past where our site is. So there would have been a lot of resuspension as they were going in and out on the high tides with the barge, but also goodness knows what they're doing on the golf course. And they've just developed a house right on the headland, and it's opposite the entrance to Hamilton Island Marina. So there is potentially all sorts of chronic pressures there. Elsewhere, I don't know how much the Daydream Island Resort would put out. There's a lot of algae there, but there wasn't before. So it's sort of come in after that cyclone. That cyclone really stirred up the conditions in the Whitsundays for a number of years. It was noticeably dirty and the substrate was silty, so it was constantly resuspending and resettling, resuspend. And I think that's finally cleared. The substrate at most of our sites now is a lot cleaner than it's been for several years. So yeah, I don't think it's such a direct input there where you've got, sort of Jeffrey Bay and the creek that runs through the middle of it picking up the old septics. Not anymore. They put it on sewage, I believe. Are they?
Yet again, a really interesting presentation which tells us of the complexity of the story, and as just pointed out, there can be a reef within cooey of each other, or it can be even a 10 metres different location and be experiencing different things. That concept of the intervention concept of removing sargassum, have we seen any evidence of that being successful anywhere?
I think there's some, they did some removals at Florence that I believe they got quite a lot more recruitment in the cleared patches than they did outside. But, it's obviously better to remove the cause than remedy it, but I think that there is the case that there's these density dependent feedbacks once you get so much macroalgae in a system that, you start to reduce coral cover, therefore you reduce propagules, and but more propagules for algae, and overwhelming any predators, herbivores, removing herbivore habitat. It's nowhere for the parrotfish to sleep anymore. Sea urchins to hide. So yeah, I think there is potentially to break out of that density dependence.
All right. Yet again, I suppose we're going, back to that situation of what the story the monitoring is telling us, and what we're going to do about that story that it tells us. And that's really our next phase that we're obviously going into, is are we going to step up into the restoration or intervention or whatever the definitions of those actions that we're going to be. And yet again, we don't know unless we're monitoring. We don't have that information.
No, and one thing that is completely anecdotal, but when I first started diving and snorkeling around Magnetic Island, you had to be careful where you put your hand because there was big diadema urchins everywhere, and to the point like piles that high where the barge used to come in Jeffrey Bay. I think there was a spawning behaviour, but they'd make pyramids. And in the Whitsundays it was the same, and they're still around, but they're nowhere near the densities they used to be. So
interesting story. We've only been monitoring, we keep saying, I know I started the day off saying we're the longest monitoring water quality program in the tropics, but really, it's such a short span that we know, and we're working with that information, which is one of the reasons why Steve's presentation was just, incredible as well. Yet again, the dedication of people involved to go to that depth to dissect data, just like Angus is trying to do, saying, okay, so if we remove all these things and we just can remove the obvious bleaching, the obvious this, now can we look at what the DIN story is or what the discharge story is and trying to work that out. So we've got still lots of things to do. And Angus will be really, really keen to hear that some of that funding is going to look at the Mary Burnett area and see if we can bring coral monitoring into the MMP, which is really good. So something we're consulting on. Has anyone got any last thoughts or comments? Martina, are you thinking of anything that... Yes. We have a think tank with our partners tomorrow, so we're going to certainly be talking about some of these things and getting some feedback on the dashboard. I believe in the agenda it fell to me for final remarks. Was that correct? Are we ready for final remarks? I am. Can I stay sitting and do it? I don't need to go and stand up there. Yep, just what we talked about already. I think the coral and seagrass stories tell us of that complexity. One of the things we didn't want to do on the dashboard is actually put the reef-wide scores or the reef-wide grades, because it's really obvious that they don't tell the story. And what are we really using those reef-wide grades for? Obviously, our government likes it. They like that sort of simplicity. They want that story. But one of the things I think we can use the dashboard for and use this program for is to make sure that that doesn't overwhelm the fact that we have to look more minutely than that. We have to look into the different regions and the different areas, and even within those. That seagrass story for me consistently is telling me when you talk to land in detail about extent, and now we have the new Oceans National Accounting System that is just, accounted seagrass for around Australia, and yet when we look at a space of seagrass, that doesn't mean it's all seagrass. It's highly variable within that space as well. So we have this whole issue with our governments like simple stories. Blue carbon is a fairly straightforward story, really, but is that being adequately representative? And without monitoring, we don't know if that's actually representative of what's happening in the Great Barrier Reef region. What else did I have here? There is no one single same baseline that applies across the reef for anything. There is, what are we trying to reach? What are we trying to go back to? What are we trying to attain? What we're seeing today is it's highly variable. We can't give them simple answers for that. The intervention, restoration story. Len, I wasn't putting you on the spot at all. I was really interested in the definitions because we're going to have to struggle with these going forward. Is what are we doing with this and how do we define that, and whether, you know, we're talking about planting seeds or planting plants or removing algae or planting corals or whatever it is that we're going to do. And the water quality story. We have to have 3 presentations to cover the water quality story, okay? A massive, massive effort. And they tell different stories as well. So those components really tell us the different stories. We can't monitor one without the other. We can't tell the full story if we just look at one and the other. And I know I might be beating around the bush here, but this year I could equate it to crawling across gravel to make sure the marine monitoring program can go on with more funding rather than less funding. And as again, I said, we just happened to be lucky that we had a change of government and I managed to talk to some of the right people, that we got that opportunity. And I think today really, really showed us the value of the marine monitoring program. And it's not the only monitoring program. We have the long-term monitoring program as well, and we have all sorts of other monitoring programs. And one of our challenges in the program that I see going forward, 2 probably really big challenges, is how do we start bringing the other monitoring program data that could be quite different and finding algorithms, finding great statisticians that can do this for us, to compare that data in some statistical way that tells us an effective story. So one of the obvious misses here today is, where's the fish monitoring? And we did consider bringing in a fish monitoring story today, but that is part of the reef and seagrass story and the water quality story, along with other animals. We've got dugongs, we have sea cucumbers, all sorts of things. But what I'd like to see in the future is, yet again, it's the one-stop shop idea, but more than that, it's the layers of these informations coming on top of each other. So when we do have to consider a spot, when we do have to consider an incident or a location, or where are we going to intervene, or where are we going to restore, or lo and behold, another ship runs aground in another reef series or whatever, that we have all of that information at our fingertips. And we can make that decision based on the work on the seagrass. What is the resilience of this area? The work in the coral, what do we know about intervention here? So I know you don't need convincing, but what I'm trying to, I suppose, get across is that you've got people working really, really hard, seriously hard, to improve this program, and we're always up for ideas and thoughts, and we're all in the same boat on this. I know in this year I've experienced some interesting commentary about, it's almost combative, you know, why did you do this, and the you know, budget's gone down and you're not monitoring enough areas. Well, I can tell you this, our predecessors actually made sure the monitoring program existed, as in it's still here today, which I think possibly it had a little bit of a blip there for a while. But also you can be guaranteed we're doing as much as we can with the money that we can get. I think that's the point. We can't do everything, hence why Jenny's here talking about modelling with us. How do we combine those 2 things to make sure we can get more of the story and satisfy, for example, my CEO, who keeps saying, can't you make it more cost effective? Okay, well, one way I did is I got someone else to pay for it. Is that better cost effectiveness? However, it's not quite the story. But so, you know, I think these days are really, really tremendously beneficial. As I said, it's Martina's and I, first time doing, you know, as our partnership, as she said, I keep saying we're new, I mean we're new this year, January. And our partners had to put up with a really different team, I gather, walking in their doors. So I appreciate that. And I appreciate everyone coming. And I'm hoping it's opened the doors for you, you know, for us to talk together, and we'll put marine monitoring program back up on the agenda. And I think we have. Anyone else? Anyone else like to say anything? Those online, are you still there? My computer died about 2 hours ago, so I can't see you. I hope you are, and if you have, thank you very much for being there. I hope we've been monitoring your comments. And I'm seriously going to call it quits and GMT time. I'm hanging around for a drink and a chat, and whoever wants to be here. Those that are coming to Longboard with us still, 6 o'clock.